your credits, you'll then be throttled, right? So that's how these are great for like bursty workloads, running low power web servers, DNS servers, those kind of things. Great way of saving money or being more cost effective. All right. So the way it's done, actually, I can't use let's zoom in a little bit. So see the naming here, T3 Nano. T is the class of family. So that's our burstable class. 3 is the generation. So this is the 3rd generation of our T-class instances. And this one is a nano, right? So the smallest T3 you can get is 2 virtual CPUs that accumulates 12 credits per hour, and you give half a gig of RAM and up to 5 gig networking. And then we double up from there. As you can see, we're doubling up actually on the gigabytes at this time. But we increase the family size, then you accumulate more credits. And that's the way it works. So we go nano, micro, small, medium, large, XL, 2XL, and then other ones will go 8XL. I think 96XL is the biggest one we've got. I think it's an M6 Graviton. There we go. So I think the biggest one, metal, actually you can run on bare metal as well. So you can have exclusive use of the complete server at the metal level. So no AWS hypervisor in there. That's pretty cool, isn't it? Anyway, so some of these, that's why. Memory optimized. So if we go for an R6 Graviton, the biggest one we've got is R6D 16XL, 500 and half a terabyte of RAM, 64 CPUs. So yeah, there's some pretty big machines out there. Quick guesstimate from you. What's the biggest machine that you can provision in AWS by CPU and RAM count? So we've seen the smallest, 2 virtual CPUs and half a gig of RAM. What do you think the biggest machine that you can provision in AWS is? Have a guess. Yeah, that's the RE class, really big. I like that. Go on, put some numbers to that, Thomas. What does Netflix? XXL? Yeah. Netflix. So actually, we're coming on to pricing next, and I'll tell you how Netflix pays. All right, so get ready for this. This one blew me away when I found out. The largest machine you can run in AWS is 446 CPUs and 24 terabytes of RAM. I think, is it this one? No, there's another one. Now, for that one, you do actually need special permission to run it. All right, it was originally designed to run SAP workloads, but we don't do any exclusive development. I'm trying to remember not that one. No, it can't run Crisis. No, it can run Doom quite well, apparently. I'm trying to remember the name of the system. It might be the Z1. Anyway, yeah, so 446 and 24 terabytes of RAM. No, that's not it. Might be the high memory. There we go. Here's the system. There you go. It's the biggest one. It's the U24 TB1 Metal, 448, 24 terabytes of RAM. Now, I don't think we actually published the pricing for that one, and I think you might need, I think you need special permission. But here's the thing, though. The fact that you can rent this by the second for testing. Imagine you wanted to test out an SAP workload, and you imagine going to finance and saying, okay, I need a machine this size to test a workload to see if we want to invest in it. How much do you think? What do you think your chances of getting that are? Well, I mean, I don't know. You're a finance company. Maybe you're going to get pretty good chances. But imagine being able to rent this by the second. Yeah, slim to none. Okay, fair enough. But now you go to your boss and you say, look, we've got this thing that suits an SAP workload. I can spend a week on this. I've got this automated install. There's actually an SAP program on AWS, but you go through the clicky, and you get this big machine and you run the demo for 2 weeks or whatever. you spend, now it ain't going to be cheap. This is going to be in the probably tens or hundreds of dollars an hour. I don't know the number, but that's got to be better than $200,000 worth of machine, right? And you just turn it off and say experiment failed or success, right? But anyway, so there you go. That's the biggest machine you can get, which is pretty cool. Right, let's go back to there. All right, any questions on instance types before we move on to pricing? No? Pretty cool, huh? All right. Now, all of these options, you're going to have to pay for them, right? The cloud is not for free, well, with the exception of the AWS free tier. So you can run one of those T2 nanos, T2 micros for free for 1 year. All right, so you're allowed 750 hours of T2 micro free for 1 year. Beyond that, you're going to pay for it, right? So how do you pay for it? Couple of ways. On demand. On demand is the most expensive way to pay for EC2. Now, I would posit that it's still a very cost-effective way, and compared to buying stuff on premise, a cheaper way of getting your stuff. But in the EC2 world, on demand is the most expensive way. However, it's the most flexible. So no upfront costs. No, oh, it's going to do that in it, yeah. No upfront costs, no minimum contracts. You turn it on, you use it, you turn it off, you stop paying for it. Short-term, irregular, bursty workloads. Now, when you're calculating all this stuff, it basically comes down to a spreadsheet exercise. So all of you Excel drivers, you're going to love this next section. You have to work out the best price point and what your billing methods is. Now, remember, this is all billing methods, all right? So on demand. No upfront, maximum flexibility, turn it on, pay for it, turn it off, stop paying for it. This one I love, spot workloads. When I tell you about spot, initially you're probably going to go, ain't using that. That sounds ridiculous. But I'm going to draw it for you, okay? I will also tell you up front that Netflix, because we had it, runs almost exclusively on the spot. Now I've lost my mouse. Come on, there it is. There it is. Okay, so let's get another white screen. Okay. AWS capacity and our average customers utilization, kind of like that. Remember I said the benefit of one of the benefits of going to the cloud is you don't have to guess capacity anymore. You've basically offloaded that responsibility to us. We need to make sure that all of our customers don't run out of stuff at any given time. So we vastly over provision. So we're probably provisioned somewhere up here, all right? Now, we are the cloud and we like being optimal. So we looked at that and went, no, that's bad. What can we do with that? What can we do with this excess capacity up here? If this was your data center, this is all wasted money. All right, in our data centers, if we didn't have the spot market, this would be wasted money, and we don't like that. So we invented the spot market. And what the spot market is you get hyper discounted access to our excess capacity. You are the bottom of the rung, though. So the caveat to using spot is that we as AWS can take away any instances that you're running on the spot market with a 2-minute notice. And that's the bit where you go, what? That don't sound very good. But think about it for a moment. Think about the servers that you've got in your data center that are stateless and can be replaced very easily. Web servers that typically connect to, an NFS drive or some other drive, shared resources to serve their content from. They connect to a database to get their data, and really all they have on them, if we're designing them correctly, is the database software. So why can't I replace it? Why do I need to pay full price for that thing that's utterly replaceable? Well, mate, I don't. Maybe I don't. Maybe I can use the spot market for that. We'll come on to how you integrate with the auto scaling, but let's just say right now, you've looked at your workload and go, you know what? I think I can use the spot market for that. So I can tell my auto scaling group to use the spot market. And the way it actually works is It's all to do with supply and demand. I mean, we're in a finance company. You can understand this one. We're in a money company. Are you a finance? No, you're banking. Anyway, whatever. The way it works is all based on supply and demand. Let's say, for argument's sake, you want an M5 dot large, okay? And the regular running price of that is $1 per hour. What we will do is we'll put our excess capacity in the spot market, and we'll say you can have that at $0.1 per hour. So now 10 cents. So you get a 90% discount. What you do when you request something, you say, this is the maximum price I will pay. So let's say you now put in there, my maximum price is $0.5. Okay. So you're prepared to pay up to 50 cents per hour to run this M5 large. All good so far? Quick thumbs up. So we've got three parameters right now. We've got three parameters. We've got regular running price, we've got the discount price, and we've got the price that you are prepared to pay. So all of our on-demand customers, they all start wanting M5 larges. So our capacity is reduced. And therefore, there's high demand in the supply and demand market. So we increase the price, the current paying price. So now we say 0.2. It's now 20 cents an hour to run it. Pressure goes up, pressure goes up, pressure goes up. And now we're at, say, 0.6, right? So we'll just scrub that one out. So we're now at 0.6. That is above the price you are prepared to pay. So to satisfy, is there a limit? It's like a, could be. Yeah, essentially, if I'm reading that correctly, yeah. So once the price goes above what you're prepared to pay, we have the option to remove it. And we just give you 2 minutes notice, and you cannot interrupt that, by the way. You can't reset your price. You lose that instance. You have 2 minutes to shut down, or we turn it off. We take it away from you. Knowing that, you can architect your systems to, now what most people actually do, and the default is they actually set their prepared to pay price at the on-demand price. Very rare does it go up to there. And you get the full history of the spot market. So I'll show you that. But does that make sense? That's essentially what the spot market is. It's an interruptible supply and demand system. Okay. Once you really get the idea that you can be interrupted and it's okay within that certain workload, you can save a lot of money. Like I said, Netflix runs almost exclusively in the spot market. But let's have a quick look. There we go. So I'm going to look at my AWS management console. It's part of the EC2 service. And so we give you the complete history. The service resumes. Your EC2 instance will not be returned to you. No. We terminate it. We completely remove it and give it to our on-demand customers because they're paying full price. Like I say, you're the bottom of the rung. Right. So spot requests. We look at the spot requests. I'm just showing you that you get the full history here. So you can make informed choices. So we've got pricing history. Now, all availability zones. Let's, what one were we looking at? Let's say an M6. M6 is a bit of a workhorse. So M6, no, M5. M5 large. There you go, M5 XL. Bit of a workhorse, date range over 3 months. Let's hope we get some. All right, so slight changing here. All right, you can see the numbers changing. Now this is done in a per availability zone, but for the purpose of this, don't worry too much about that. But if you look up here in US East 1F, you can see the price is fluctuating. And you can see that you got an average saving and this one of 65%. So it can be significant. And if you bid at this one, it's not called bidding anymore. But if you put in your price of 0.2 cents per hour, given this 3-month period, your likelihood of actually being interrupted looks pretty zero to me. What's our normalized? Yeah. All right. Does that make sense? It's a pretty cool way of paying for things. But it only works if your software can afford to be interrupted. All right. Okay. So that's the spot market and the on-demand prices. We've got other choices, though. We've got reserved. Reserved is a bit legacy now. Is that going to? Yeah. So reserved is legacy. Our customers said, I don't want to pay full on-demand price for things that are going to be steady state and going to be running for years. So we said, great, you give us all the money up front and we'll give you up to 72% discount. So that's essentially how it works. They are quite restrictive though. So they were invented quite a while ago, or the concept was released quite a while ago. And so it's tied to a particular EC2 instance type. So let's say we stick with our workhorse M5 large, and it is tied to an availability zone. And if you're not familiar, don't worry, we'll come on to that. So if you need to deploy that instance somewhere else, you can't, right? So it's a great way to get discounts for steady state workloads that are not really dynamic, they're not mobile, they stay in where you deployed them. 1 or 3, I don't know why there's no 2, but you require a 1 or 3 year commitment, and you can choose to spread the payment over your commitment term, or you can give us all the money up front. Yes, they could. Yes. It is still legacy, but there's also, you can sell your reserved capacity as well on the reserved instance market. But if you're talking to a TAM or an SA, a technical account manager or an SA, they're going to recommend nowadays these ones, your compute savings plans. Compute savings plans are more flexible. So instead of being tied to an instance type in an availability zone, you're committing to a spend. So now you can say, given my workload, I think I'm going to spend something like, I don't know, $2,000 an hour. And that's where you get your discounts. If you go over that, BMO's do. Yep. Yeah, fabulous. Yeah, compute savings plan. That's definitely the way to go. All TAMs are going to recommend compute savings plans now. Yes, awesome. So yeah, you're committing to spend. You're not committing to a particular hardware configuration in a particular data center, essentially. So it's much more flexible. So yeah, that's what your TAMs are going to recommend. Now, for some workloads, the cloud essentially is a shared tenancy agreement, right? So when you schedule an EC2 instance, it's just placed out there in the general populace. It's all isolated, nobody can see each other, so don't worry about that. And it's not a noisy neighbor scenario, but you are on shared hardware. You could be sitting on an Amazon owned server that's shared with other customers. In fact, you are going to be. However, there are some regulations that say you must be on single tenant hardware. And so for that, we have a dedicated instance. Now, what that does is we look around our infrastructure for a piece of hardware that doesn't have anybody on it. And then we give it to you. But this is non-permanent. So the moment you remove your EC2 instance, then that server goes back in the pool. All right. So it satisfies our single tenant requirement, usually for regulatory requirements. But remember, once the last EC2 instance has gone from that physical server, it's put back in the general populace. But there are other times where we want to keep exclusive use of a server. For that one, we've got a dedicated host. Now, what that means is we look for an AWS hypervisor that is free, and we exclusively give it to you until you give it back. As it says here, it's the most expensive because you are reserving a complete server, whether you're running anything on it or not. The biggest reason you would do this is for very punitive software licensing, because some software licensing is tied to CPU IDs. And so you cannot move it to another virtual machine because your CPU ID changes. You cannot put it on this dedicated instance because the next time you release it and then go and reschedule it, your vCPU ID is going to change. So this one is usually for compliance, and this one is usually for software licensing. But you do have the option to run in single tenancy should you need it. All right. Knowledge check. In fact, any questions for me before I ask you these series of questions? Oh yeah, absolutely there are. Yep, lots. There's lots. Lots of people have not updated software. One of the Oracle is a big one. That's why I think that may be one of the reasons they're pushing the Oracle cloud. Yeah. In fact, they make it pretty hard to run anywhere that is not on-prem, excuse me, or Oracle. But they're certainly not exclusive. There are many other pieces of software that are CPU bound. All right. So my question to you, what's the difference between savings plan and spot instances? Anybody want to pop up on the mic to answer this one? It might be easier than typing.
Yeah, I'll go. This is Tom.
Thanks, Tom.
Probably the biggest one, I think, with compute savings plan is a commitment to spend.
Yep. Whereas the spot instance is...
Well, yeah, spot instances, if it's available at your price, you can use it, but you don't have to.
Yeah, so it's more like an on-demand type system. You use it when you can get it, but maybe not if you don't need it. But that's a great question there. Why would Oracle do so? I can't answer that because they've traditionally made a lot of money from very expensive licensing. Yeah. And it may be hard for them to compete in a different pricing model. That's going to be my guess, but yeah. Pay as you go versus commitment to pay. Yeah. And yeah, they don't yet have a better model. They may not even want to develop a better model because they've got, recurring revenue from expensive licensing. I can't speak to their business model, but that's why there was a very public battle, I guess, for want of a better word, between Amazon.com and Oracle. Amazon.com made a commitment 10 years ago to get Oracle out of Amazon.com because it was too expensive. Anyway, so yeah, you're right. Compute savings plans for workloads, consistent amount of compute over 1 or 3 year terms. Yep, spot instances are flexible and can withstand interruptions. So yeah, correct. Okay, the Holy Grail, Amazon EC2 auto scaling. This is, I think, reason number 2 why most companies or people consider the cloud. The first one is they assume it's going to be cheaper. Hopefully it's more cost effective. We don't like the word cheap. And the second one is elasticity, this scaling piece. So what is auto scaling? Well, auto scaling basically means the ability for your infrastructure to change as requirements and load go up and down. All right, so we don't want to be running capacity when we're not using it. So if we look at this is inefficiency, right? This is badness. We don't like that. That's all money wasted. What we actually want is our infrastructure to match without clipping. All right, we don't want to clip. What's the term? One's a lost opportunity, one's I can't ever remember the exact terms. But wherever you have this piece here, that one's a lost opportunity. No, that's a cost opportunity. And if you clip like that, then you've got a lost opportunity because you've got annoyed customers there. And this one is money spent where you don't need to. So what we really want is our infrastructure to match our demand. So for that, we use EC2 auto scaling. EC2 auto scaling basically has a couple of elements to it. When you configure auto scaling, let's say you're going to run a big website, right? You're shopping or you're an online bank And behind the scenes, you only want to run the amount of servers required. So great, we're going to use auto scaling. You've made the choice. So you look at the numbers, you look at your predicted load, and you say, you know what, we are never going below 10 servers, right? So that you configure your auto scaling group with a minimum of 10. You'll never go below that. If you're running at the minimum, let's say you are running, it's the middle of the night, and you're running 10, and all of a sudden 2 of them crash, auto scaling will auto heal them. All right, so it will just remove those 2 damaged ones and replace them, because we've told the auto scaling group always maintain a minimum of 10. All right, so it's responsible for maintaining that. The other thing that we tell it is the max. So this is where we look at a dimension that's important to you, transactions per second. CPU is a common one. So I never want to, I've looked at my workload and I think I can fit them all within 100. So this is 10. So that's our operating range, between 10 and 100. That's our mins and maxes. This is where the forecasting comes in. Remember, what we haven't done, we haven't looked at individual servers. What we're looking at is our parameters. So that's what we've done. We've got 10 and 100. But how does the system know what to run at any given point? Well, for that, we program the auto-scaling policies. And we'll just keep a real simple one. CPU. If we put a rule in there that says if CPU across the current running set of servers goes above 70%, then make some more. All right, so this is our scale as needed piece, all the way up to the maximum. So as the load goes up, we start adding servers, adding servers, adding servers until we reach the maximum. Now, obviously, when you're doing maximum, you don't want to cut it so fine that you haven't got a bit of a buffer. But if you've worked out that it's 100, what would be the problem in making this 200? Well, none, really. It doesn't cost you anything to write 200 in your template or your policy. But it does mean that you've got 100% overhead should you need it, right? So you can always burst higher if your system gets bigger and busier. And then, so we have an inverse rule that says if CPU across the current running system gets below 30%, then start removing instances. All right. So it's all based on load, and CPU is just one of the metrics we can use. So that's the basics of how an auto scaling group works. Which is pretty cool, right? No operators involved. You just program it and you let it carry on and do its thing. Now, where does it say it? Here we go. A couple of methods that we have. We've got dynamic scaling and we have predictive scaling. These are all to do with the scaling policies. Dynamic scaling means look at the load and react to it. So it's good for spiky, unpredictable workloads like that, all right? So we can follow that, and the auto scaling will try and make the infrastructure match, what our demand curve actually looks like. The other one that we've got in my messy screen is predictive scaling. Now, predictive scaling, if you had a demand curve like this, predictive scaling would be fabulous. And what it does, it doesn't wait for the system to get busy before it starts creating infrastructure, right? It will look at this and it will start creating infrastructure like this. You can still influence it, but it's basic. That's what it does. Yeah, there are some rules on how you scale, but I mean it's not for this course. But yeah, absolutely. I've just given you the overview. There's a lot of configuration on how much to scale at any given point. There's different scaling policies like target tracking, step scaling, those kind of things. There is a lot of flexibility in that, and also in your payment methods as well. So for example, you can say everything up to here, use my reserve or my savings plan. Anything above that, use the spot market. So there's a lot more flexibility than what I've just told you in these couple of simple slides. But yeah, so predictive scaling looks back 1 day and 7 days. And as long as, like I say, as long as your curve looks like that, it will start pre-provisioning infrastructure. So you've got no surge queue, essentially. Pretty nifty, huh? All right. Any questions on auto scaling? Leonard's a fan. Leonard's all in now, I can tell. All right, elastic load balancing. It's no good having having these 100 web servers down there if, remember the old days, you do DNS and you put all 100 of those in an A record. So from www.stuartfox.com would have 100 IP addresses. That's not very good, is it? Because when your auto-scaling group kills those, we've now got to update DNS and remove half of those. And now my client, which is my web browser that's accessing Stuart Fox's amazing website, by the way, it's amazing, then it's got wrong addresses. That's not very good. So years ago, we solved this with load balancers. So www.stuartfox.com resolves to one IP address. That is our load balancer. And then the load balancer takes care of who it's going to balance to. We've been doing this for years, right? Okay. So we have that service available in AWS called ELB, the Elastic Load Balancing Service. Automatically distributes across multiple backend resources, yes, and gives us a single point of contact. All right. Now it works together with oh, there are loads of TLAs, and I did apologize for that. So EC2 stands for Elastic Compute Cloud. So basically virtual machines. Correct. Auto scaling. Adding a second EC2 instance during a popular sale. AS or ELB? More TLAs. Yep, correct. Distributing work across multiple EC2 instances. Stand straight in there. Yep, ELB. Ensures no single instance has to carry the full workload on its own. Load balancing. Yep. Automatically adjusting the number of EC2 instances to match demand. Oh, I think we caught Leonard out there. Yeah, that one is auto scaling. Auto scaling tells the load balancer which instances, but it doesn't do it. The load balancer doesn't do it itself. Provide a single point of contact for traffic into an auto scaling group. Yeah, that is ELB. Now, one thing I do want to tell you about ELB, it is not a single point of failure, right? This is not a device that you provision. This is a service that you use. So don't think you have to provision two ELBs like you would in on-prem. You buy two F5s. Don't need to do that. You configure the load balancing rules. We take care of that under the hood, right? That's all on us. HA, highly scalable, redundant, that kind of stuff. So it's not a single point of failure. All right, messaging. How do we decouple? This is a big thing in cloud and actually modern software architecture. One of the methods that we can use for breaking apart these monolithic applications is to break them down into microservices. You've probably heard it in AWS and in Amazon. Actually, there was an email went around. It's something like 2005. I can't remember, but a long time ago, from the boss, from Uncle Jeff, that said, you will do microservices from now on, right? It is a top-down edict in Amazon to run microservices architectures. We are not allowed to develop monolithic applications. What does that mean? A monolithic application means all functions are basically bundled into one process. Classic, and I'm not picking on Java here. This can be done in any language. But imagine you run your application server in a say Tomcat, and all of the functions in a single jar file, and so they all run in that same process space. Maybe easy up front to develop that, but over time it becomes less performant, harder to maintain. Lots of reasons for not running monolithic applications. Modern way then to break apart that is to use these microservices. And now what we do now is each one of these components runs as an independent service. Here's the difficult thing though, is in a monolithic application, communications between 1 and 2 and however it needs to be, like that, they're all handled internally, shared memory, IPC, local shared directory, whatever it happens to be, it's all local. But obviously, if we break apart the monolith, we still need the communications channels. And so we've got various methods to do these inter-component message passing. We've obviously got one where, component 1 could be behind a load balancer, all right? So that's running multiple services. And another service is running, behind a load balancer, and they talk through the load balancers. So they're doing HTTP calls to each other. That's one way. That would give us synchronous communications. But sometimes we don't need synchronous communications. We can have asynchronous communications. So for that one, we can use message passing. And we have 2 services. Actually, we have 3 services, but I'll tell you about the second one after these 2. We have simple notification services, which is a one-to-many broadcast system. So a producer, let's say your application, writes a note, puts it on what's known as a topic. So if you've ever done enterprise service bus, you'll know exactly what I'm talking about. And you have multiple subscribers to this topic. So as the message flows in, every one of the subscribers gets the message. They can all do different things with it. So let's say this is a purchase happened, right? So the message goes into the topic that customer X has purchased a product. All of the downstream subscribers get the message. This one could be the payment gateway, all right? So that goes off and charges their credit card. This could be initializing the factory or the warehouse to go and pack it into a box and put it on the truck. Now I'm going to try and attempt to draw a truck. There you go. I'm going to put it on the truck. And maybe this one is an email notification that goes out to the customer that says your product has been packed and is on its way, right? But the fact is that we had one message that initiated that complex workflow. That's the basics of a notification system or a topic-based system. The other one that we have is a queuing system. Now, a queuing system is a one-to-one relationship. Now, what that means is that a message is put onto the queue and only one consumer has a copy of the message, right? So it's up to that one consumer to process it. There are safety features built in. So if this crashes, the message is not lost from the queue. So don't worry too much about message safety at this point. We cover it more in the developing class. Hopefully I'll see you in the developing class. But so this is a one-to-one system, and it's a store and forward system as well. So this one can store messages for up to 14 days. All right. And we can redeliver it. So if this one fails, another consumer comes in and says, give me a message, we will give it to that consumer. All right. You have full programmatic control over that, on how long it's kept for and how many times it's out for delivery and all that kind of stuff. But at this point, don't worry. So this is a queuing service. Now this one allows us to, or both of these allow us to completely decouple. This web server here has no knowledge of the downstream systems. And the downstream systems have no knowledge of this web server up here, all right? They are decoupled and asynchronous, all right? So that's modern architecture in a very quick nutshell. Any questions before we hit the other bit of fun in compute, which is serverless? No, simple is a design principle for most of the AWS services. If you think about, if you ever run like JBoss or, not OpenNMS, I've forgotten it. Anyway, one of the, say, MQ series, yeah, any of those are complex beasts, all right? ActiveMQ, that's the word, OpenMQ or MQ series, yeah, any of those. Those brokers are complex pieces of software that require very careful crafting and running and monitoring and wiring up. They're very powerful, and very feature rich. But how many of the features do you tend to use in these pieces of complex software? Actually, very limited. And so the simple in this is we design services that are not overloaded with features that most people don't need. And so let's go back to the topic, SQS, right? So this one here, SQS. If you've ever run, like I say, things like JBoss messaging, OpenMQ, ActiveMQ, RabbitMQ, any of those, maintaining broker software and routing between here, getting failover going and all that kind of stuff is complex. So I would call that a complex queuing service, where really what you want, the functionality that you want, is to be able to put a message on the queue and have it delivered to somebody else. That is what you actually require. So it's not really marketing, it's actually a design principle. We will keep this service as simple as we can and build in features that people want. There you go. So there's my answer on why we put simple in the title. It's not that it's limited, it's just that we've simplified it to have only what's needed. All right, serverless, love this one. As an ex-data center operator and designer, I appreciate this more than I thought I would when I first heard the term. I used to love going into my data centers and doing the racking and stacking and getting in there and getting underneath the floorboards and wiring it up and all that kind of stuff. Servers are cool, but they're not cool. Actually, in data centers, it's really cold and noisy, and they're not fun places to be. And managing servers and managing infrastructure actually takes a lot of effort. But do we need to do that? Well, maybe not. With computing virtual servers or even physical servers, you've got to do all this. You've got to maintain the servers and the infrastructure, which includes the networking, including the HVAC, and blah, 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 all that kind of stuff. It's not my core business. Do I need to focus on it? No, probably not. What do I need to focus on? This. This is where my money is made, is in my code, my workloads, my application suites. So the whole idea of serverless computing is that we remove the server piece. We still need code, we still need applications, workloads, whatever it happens to be. All we're doing is saying, you run the work, you run the servers, I don't care. I want the code to run. I want my workload to run. Oh, cat's going crazy. So that's what serverless is. It's computing without servers. Now, we're not so magic that we can run your code without servers, right? We haven't actually got to full serverless computing yet. All it means is you don't run them. All right. The primary method right now of consuming serverless compute in AWS is through a service called Lambda. Now, think about how let's say the stuff that you need to do to run software on-prem, okay? You need the servers, you need deployment mechanisms, you need monitoring, you need this, you need that, you need patching, and you need people to run the physical servers. With Lambda, you don't do any of that. And yeah, Glue, yep, that's another one, yep, for ETL operations, absolutely. But for General compute, Lambda is probably the more common compute service that we have, or serverless compute. And so in this one, you don't even manage the runtime. So if you're programming in Java or Python or one of the supported languages, you literally just give us the code and we manage everything from the runtime downwards. All right. Your code only runs while it's you only pay for your code while it is running. And what that means is it's part of event-driven computing. So let's say you have an upload to an S3 bucket. We'll cover S3 later, don't worry. You have an upload to S3. That we then send an event, which means something has happened. Now run my code. Now you tell AWS what that event, what those mappings are, but something happens, run my code. When your code has finished running that function, it will actually stop. It will terminate. All right. So you're not paying for long running services. If you optimize your code that it runs this event and processes it in 20 milliseconds, what do you think you pay for? 20 milliseconds of compute. That's it. AWS Lambda now builds you down to the microsecond. So that's it. You are now heavily incentivized to optimize your code to run as efficiently as possible. So, but you can now get to focus on that because you ain't worrying about all the other stuff that you needed to worry about before. All right. You give us your code. You tell us the runtime you want. You tell us what event and under what conditions to run your code, and then we run it for you, and then it turns off. All right. So that is the basis of Lambda. How does it work? Simples. Upload your code. Tell us when to run your code. Your code runs, and then it turns off. I love it. It's great. Now, it may think, oh, well, you can't run stuff like that. Like, how am I going to listen on the network? You don't listen on the network. It's not a network service, right? It's not a daemon or a Windows service. This is part of event-driven computing. Event-driven and serverless are not the same, but they are kind of co-related. And so we can have reactive workloads. So your code itself does not monitor the trigger. The AWS Lambda service has integration points. It's used. Yes, it can be used for user-defined functions in SQL as well. Yes, in Aurora. Yep. So we can have the equivalents of stored procedures and stuff like that are done by external compute. Yep, absolutely. So go back to that. Your Lambda code, your code does not monitor anything. We have service integration. So again, let's say that service integration is AWS S3 accepts a file for upload. S3 then gives an event to the AWS Lambda service, and the Lambda service knows what to do with that event in your account. So then it runs your code for you, but your code does not do monitoring. Your code only runs. It's given the event actually through standard in. So it's given a text-based event, which runs and then shuts down. So yeah, you don't do monitoring of events. It's pretty cool. You don't even have to do that. You don't have to write any network code at all. It's great. You literally accept in a JSON document through standard in and you process it and then you exit. Pretty cool. All right. Any questions on Lambda? Lambda is a big, big subject. If you are interested in getting deeper knowledge of serverless and event-driven, we've got developing serverless solutions, another 3-day course. So yeah, there's that one if you want more information. All right. Next one, containers. Containers have been around for a very long time, and it's kind of that middle layer of abstraction between running a virtual server and running serverless, as we just saw. Containers kind of, you don't have to run full operating systems, but in general, you manage the runtime and the application. So in Lambda, you just run the application or your code. We take care of the runtime. In containers, essentially, you bundle the runtime and all dependencies into, think of it as a zip file, and then excuse me, and then we run the containers for you. It sounds a little bit like packaging MSIs, but the difference is containers or containers run isolated. All right, so what we can do is we can it's called bin packing. How is monolithic different? 1 second. That's a great question, actually. So a monolithic application contains many functions. Containers is one of the methods we can use to implement microservices. So what we can do is take that monolithic application, we break out the individual functions, and each one becomes a container. So they have traditionally gone hand in hand, containers and not serverless. Breaking apart microservices, that's the word. But they are, I mean, you could run a monolith inside a container, absolutely. They're not the same, but they are correlated. All right, yes. So one host, multiple containers. Yes, we have a server, that's your physical server. You have an operating system that runs Docker, is probably the most common one that people are aware of. And then inside the container, you contain your application and the libraries. How is it different to virtual machines? Well, in here, in a virtual machine, you've got a hypervisor layer and you've got a BIOS, a virtual BIOS, and you've then got a full operating system. All right. So there's a lot of inefficiency in running virtual machines. We can very efficiently pack our individual server with lots of containers, which is great and really easy to do by hand if you have one server. But what if you're like most companies and you have hundreds of servers all running containers? And this is container one that's actually we want scheduled over here as well for redundancy, and over here. And when our system gets busier, I want to run a container over there and there and there, all running the same code. Right? So it's kind of like auto scaling, but we can do it at the container level as well. And we can also correlate these. So we've got microservice number 2, that could be over there. So we can run fleets. But do you want to do that by hand? Is an isolation, let me read this one. Is an isolation of application on OS virtual machine? No, it's isolation in the kernel. So if you're going to get really nerdy, it uses Linux kernel namespaces. It's not hardware isolation, no. It's done in kernel. But it's, yes, in that case, yes, it's done in kernel, yes. Docker manages the kernel. So if you've heard of Docker, you'll know what I mean. But Docker is a container management system that makes it really easy for you to manage the containers, but it does the heavy lifting of programming the kernel to run your container in isolation. So yeah. Oh, so actually, no, you're right. Sorry, you are isolation of application in the operating system. Yeah, and virtual machine is isolation on. Yes, so virtual machines can use hardware isolation and virtualization. Yes, but containers do it all in the host operating system kernel. Yeah. All right. So back to the question: do you want to do that by hand? Of course you don't. We don't want to do things by hand. For that, you need an orchestration service. So we have 2, and I'll bring them up. They do essentially the same thing. This one was written by AWS. This one was originally written by Google, and then there's open source, so Kubernetes. They essentially do the same thing in that they manage your container orchestration. So placement, running, monitoring, all that kind of stuff, load balancing, all of that. So they all do the same thing. This one is an open source product that our customers wanted to run because Kubernetes is a very popular piece of software. This one was written by us before. I don't know which one came first, to be honest, but so this one is in by AWS, and this one is open source. Now, this is me personally, and this is just a personal recommendation. I will go here first, unless I'm doing a migration for, say, on-prem Kubernetes or another cloud provider Kubernetes, and I want to stay within the Kubernetes ecosystem. All right, so that's my personal choices. Kubernetes is open source, is very powerful, very complex. And so, yeah, I tend to lean towards simple unless I have a compelling reason to go with Kubernetes. But the choice is yours, obviously. And now to muddy the waters, remember, these are orchestration services. These take care of the placement. There are a lot of pros and cons, absolutely. Yeah. And again, we can't really cover it in this course. There's a whole course on running, I think it's a 3-day course for running Kubernetes on AWS or EKS. So yeah, it is a complex subject. Me personally, I'm leaning simple as much as possible. Now, to muddy the waters, these are the orchestration layers, right? Which means they must have infrastructure to deploy their containers to, all right, to manage the workload. Now, for this like host or execution layer, we have two choices. One of them, we can have EC2 instances. So ECS, so we're in acronym hell, or at this point, I apologize. So ECS and EKS manage or can manage a fleet of EC2 servers for you, and it will push the containers out as it deems fit, all right, based on your programming rules. But it does mean that you're running in your account fleets of EC2 instances. Now, we also have the choice to run this thing called AWS Fargate. So let's take it back. Oh, wrong one. Let's go back one. Clear my screen. Remember, these are orchestration layers. The other option for our execution environment is AWS Fargate. Now, instead of running fleets of EC2 instances, this service, AWS Fargate itself, runs a hidden fleet of EC2 instances in the AWS Fargate place somewhere. So now your orchestration systems can talk to Fargate and say, run this, and I want 50 of them. So now ECS and EKS do not have to run fleets of EC2 instances. So you're paying for the resources that you consume inside Fargate. The other option, remember, clear the screen again. These could be running fleets of EC2 instances. Remember, that's the other deployment method. You're paying for the actual EC2 instances, no matter how you're using them. Okay, so slightly different billing model. Again, I'm going Fargate initially because it's simpler. I got my orchestration layer, and I want to use Fargate because I only pay for the resources that I consume, and I'm not paying for servers, and I don't have to worry about the administration on servers. So I get, this is where it gets funky, serverless containers with a management layer. It's me personally. That's where I'm going to go. Does that make sense? Because we're at the end of this module. Everyone ready? A couple of questions for you if you've got none for me. Here we go. A, B, C, or D. Right, a customer wants to use an Amazon EC2 instance for a batch processing workload. Which EC2 instance type should they use? You choose. Yeah, compute heavy. Yeah. Basically, we're using lots and lots of CPU. Your workload could be any of those, but that's the official answer. Yeah. What are the contract length options for reserved instances? 1, 2, 3, 4, or 5. Select any two. AC, BC, AC, AC/DC. No, we haven't got that one yet. Yep, it's 1 year and 3 years. I don't know why there isn't a 2-year. I don't know. I'm not sure. But 3 years is the maximum, so those don't count. All right. 1 and 3. A customer has a workload that will run for a total of 6 months and can withstand interruptions. What would be the most cost-effective EC2 purchasing option? Yeah, so the key one there is it can withstand interruptions. Now, if it didn't say that, customer has a workload that will run for a total of 6 months, what would be the most efficient? Now, this is where you get your spreadsheets out, all right? Because it may be on demand. it may also pay you to buy a 1 year reserved instance. I can't tell you which one will be right because you've got to run those or add it to your savings plan. All right. But you get to do that. So remember, these are just billing concepts. You get to run your spreadsheets to work out which is the most cost-effective way of paying for that workload. All right. Oh, done that one. A customer wants to give users messages for the specific topics to which they have subscribed. Think about a shopping site when somebody says, notify me when this thing happens. Which one is a broadcast system? Yep, we're all in there. SNS. Yep. All right. That, ladies and gents, is the end of this module. Let's take a break. Let's be back at 11:35. All right. So we got like 7 minutes.
Hey, Stuart, quick question.
Yeah, of course.
Anything, by the way, hi.
Hi. Sorry, you're very quiet there.
But you can't hear me? Can you hear me better? No?
A little bit. I can hear you, but it's very faint. I'll lean in.
Rain set. I'm in the office today, so I don't think I've gotten a full hold of how these things work yet. But did I miss anything in terms of setup? The first half an hour? How long is this break? Check.
We'll be back at 11:35.
Okay, cool.
Cool.
Thanks.
Gaurav, you joined late. Yes. First. Yes. At lunchtime, I will release this complete slide deck to you. So yeah, don't worry about that. Okay, everybody, it's go time again. Quick thumbs up if you can see and hear me. All good. Awesome. Thank you very everyone. All right. Any questions before we move on to global infrastructure? Nope. Awesome. All right. Let's have a look then. Okay. What we're going to look at in this one, we're going to look at how the AWS global infrastructure benefits you. We'll look at availability zones and regions, CloudFront edge locations, and then how a couple of ways that you can provision these services in the regions that we're talking about. So first up, we're going to actually dive off to a website. And we're going to talk about the massive...
This might answer your question. I know about one coronavirus, COVID-19 Delta variant.
Okay, Alexa, stop. Sorry. Yeah, sorry about that. Alexa was telling me all about COVID. I don't know why she did that. Anyway, she did. So let's look at all the global infrastructure that we have. So right now, and I'm going to tell you this one as someone who's tried to do comparisons between cloud providers. Be sure when you're checking cloud providers that the terminology equates to the same thing. The big case in point is availability zones. What we class as availability zone is different to what the other cloud providers class as an availability zone. So I'm not going to say which ones or tell you which one is better than the other. All I'm going to say is when you're doing a cloud comparison, make sure you're comparing comparable services, not terminology. All right. There tends to be big differences on how we call things. Right. The reason I say that is because we use the term availability zones to, we'll come on to that in just a second. But so right now we have 26 launched regions. All right. So what does that mean? That means that across the globe, all of these blue dots are places where we have regions now. The orange dots are where we're going to be deploying regions within, I think, towards the end. So far is out to the end of 2024. And so right now we have 26 in production regions, and we have 8 regions coming soon. Case in point, for Canadian customers, we have Canada West coming at the end of 2023. So that one's about 18 months out. That's going to be in the Calgary metropolitan area. And so that's what a region is. It's a collection of AWS resources in a metropolitan area. So over here, we've got Oregon. That's actually around the Portland area. We've got Northern California. Not exactly sure where that one is, but it's Northern California, that geo. Then we've got GovCloud, which is where government and government contractor workloads run. And we've got a GovCloud on the other side as well. Can't say the word. Ohio, that's it. Yeah, see when they're launched, it tells you the different availability zones. So that's the regions that we have. These are the big metropolitan or geos all over the place. All right, with another 8 coming soon. Now, a region is made up. Oh, we're in the Middle East. So Bahrain. Hold on. No, where's it gone? Wrong place. So we've got Bahrain coming and UEA. Sorry, Bahrain is in deployment now, and UEA is coming soon. I don't have a delivery date for that. So that's where we're at the moment. We've got Israel coming up soon. We've got Melbourne. Is it Christchurch? Auckland, that's it, yeah. So a lot coming, and this will change. By the time we get to the end of 2024, there'll probably be other ones on the list as well. All right, so that's our current regions. A region is made up of availability zones. So let's go and look at availability zones. Right now, in our 26 regions, we have 84 availability zones deployed. The other stuff I'll come on to in just a second, but first, I want to go here and bring up another white screen. Okay, so a region. Control P. Stuart can't drive technology sometimes. There we go. So a region is this geo, okay? So let's say we've got this geo, and this one will be the Oregon region. The Oregon region, which is also known as US West 2. That's its internal designation. US West 2 is made up of 3, actually it might be 4, but we'll just say 3 for now. 3 availability zones. Now, an availability zone is an isolated, so they're completely independent of each other, collection of one or more data centers. So inside each availability zone, there is one or more physical data centers. And I'm just drawing 3 on each. I don't actually know. AWS does not publish these numbers. We tell you how many availability zones are in every region, but we don't tell you how many physical data centers make up those availability zones. So within one availability zone, we've got lots and lots of high-speed networking, low latency, and you will not see any latency if one web server is deployed there and the database server is deployed there. Right, this is super high speed, super low latency networking within an availability zone. The availability zones are also connected through high speed networks, but there is typically, so heard 80. No, actually it's not quite. No. So the number that you may have heard there is each one of these data centers has somewhere between 50 and 80,000 servers. But yeah. But yeah. That's a lot, isn't it? No worries. So yeah, some of our big ones, they may be multiple data centers. Some of them will be single data center availability zones. Now, the thing is that you will never know how many data centers are in an availability zone. The important thing to know is that across availability zones, you're typically, and these are not published or SLA numbers, typically you're looking at 1 millisecond latency. So, there are physics involved. These are far enough apart to take account of fault lines, geo flooding, that kind of stuff. So even at 1 millisecond, you can afford to do synchronous replication across availability zones. So that's how they're done. So we've got a region is made up of 2 or more availability zones, and an availability zone is 1 or more physical data center. The lowest level of granularity that you have access to is an availability zone. All right. Now, given that we have 26 regions, how do you know where to deploy? How do you know where to go? Well, this one is what I call the first filter. And really, it's the only one that not actually matters. That's not true. But it's your first filter. So you look at all of the available regions. We've got 26, and you go, okay, this regulation says I must have country sovereignty, okay, and I'm operating in Canada. So right now, my first filter would give me only the Canadian region. In the future, you're going to have a second one as well. Obviously, if you're operating in the US and that one says sovereignty, you've got 4 data centers plus, 4 regions plus 2 GovCloud regions. So you've got more choices there. Whatever is left after going through your first filter, you then choose any or all of these that are important to your workload. So if you're latency sensitive, with what's left over from your the first filter, pick the closest one. This one is really important. At this level where we're talking foundational services, this one doesn't matter quite as much because they're going to be in every region. However, if you're using a more advanced or cutting edge service or a recently released service, it may not be in every region. In fact, they're rarely released in every region. So if you're using AI or ML services, there's a good chance that the service is not available in every region. So check. And the last one is pricing. If you're cost sensitive and you're not latency sensitive and you're using core services, well, then push it out to the cheapest data center, which tends to be the US data centers and the Irish data center. I keep saying data center, I mean region, I do apologize. Every region has the same pricing formula, but different numbers. So operating in Sao Paulo, so if we go back to our thingy, if we look at our global map, and we look, oh, dropped it. We look at Sao Paulo, you've got 3 availability zones, but it's also the most expensive data center we operate just because business taxation in Brazil is very, very high. All right, so it uses the same pricing formula, but the numbers are different. So just be aware of that when you're choosing where to deploy, because they will have different cost implications. All right. Oh, availability zones I've kind of done. So yeah, here we go. Here's your region. Here's your availability zone, and then you've got the physical data centers that run inside it. This was taken from a website that's gone now that was really cool. It's called infrastructure.aws, and it gave you an interactive map. So you could click on these and it would zoom in, but it's gone now, unfortunately. But yeah, so that's your regions and availability zones and how they relate to, excuse me, how they relate to data centers. We recommend that any of your production workloads you deploy in a multi-AZ configuration. So in this one, we're just saying US East 1 or US West 1A. For an HA deployment, you would deploy in more than one availability zone. So that's pretty much it. If one fails, you can deploy over there. You've still got one available, ready to go. Is data housed in a particular region also bound to the legal frame? Oh, that's a good question. Right, so yes, a region is wholly in a country, yes. It would be possible, yes, it would be possible that if you are operating in Monaco, that we don't have compliance for sovereignty in Monaco. Yes, that could be the case. The data be housed or stored in a particular region. So you have, so on that, your first question there, Leonard, you have full control over where your data goes. If you put your data in US West 1, under no circumstances will we, as AWS, take it out of that region, unless you tell us to do so. So if you want cross-region replication, we will do that, but we will only do it when you tell us. So it's wholly contained in a country, and your data is wholly retained within a region unless you tell us to push it somewhere else. So yeah. All right. What is the relationship between regions and availability zones? Anyone going to do the mic?
Yeah, sure, Stuart. So each region has multiple availability zones.
Yep. Do you remember the numbers?
The number of availability zones? 84.
We do have 84. Yep.
Right.
So the way
26 regions.
Oh, nice.
Awesome. Yeah, you've got a fistful of virtual stickers. If you were in class, you'd get real stickers for your laptop because they're super cool and nerdy, right? Yes, so the numbers that we say is every region has a minimum of 2 availability zones. I believe that every new region, and has been for quite a while, gets a minimum of 3. And in fact, I think all of them have now been upgraded so that none of them, as far as I know, have 2 availability zones. But that's our official stance, is that every region will have a minimum of 2 availability zones. Okay, that's it. Cool. Thank you. All right. So that's our regions. We have a bigger reach than that as well. Minimum. Yes. Excellent. Thank you, John. We have a much larger reach than just the regions. All right. So for that one, we have a content distribution network and edge locations. Is anybody familiar with Limelight, Akamai, Cloudflare, Fastly, all of those? CDNs have been around for a very long time. We have a solution for that, and ours is called CloudFront. Around the globe, we have over 310 edge locations. We have 7 regional caches as well. So we all know how CDNs work. It's basically getting your content out to a cache as close to your customer as possible, because this is the hop that minimizes their latency. If your customer has to go all the way around the globe, there's only limited bandwidth available. Remember, bandwidth is a function of packet size and latency. Okay, so the shorter the latency, the more data we can stream to them. All right, that's the goal. Now we have 2 layers of caching. We have an edge cache, and we have a regional cache. Your content will be put into the regional cache first, where it has a longer time to live, and your edge cache, which is right close to your customer, will go to the regional cache first before it attempts to retrieve the data from your origin server. The whole point is we want it out there in cache for as long as you decide, all right? Because it keeps our customer experience much better. So yeah, we have CloudFront as a CDN as well. We also, now this is really cool, we have AWS Outposts. Has anybody heard of AWS Outposts? Yep, it's pretty cool. All right, you haven't? Oh, be prepared to be amazed, Murray. Instead of you going to the cloud, there you go, we bring the cloud to you, all right? So essentially what Outpost is racks of AWS equipment in your data center controlled via the AWS Management Console. Not every service is available, but the core networking, containers, I think S3 databases, networking, EC2 instances. Now, the really cool thing is that you manage that rack in your data center exactly the same way as you manage your cloud infrastructure. All right. You don't manage the hardware. AWS takes care of that as part of your Outpost contract. We take care of the hardware. You just use it as the cloud, but it just happens to be in your data center, and it can access your data center resources as well. All right. Good thing is your automation, your cloud formation, your automation, your scripts, your monitoring, all of that is all done. See, look at that. So Thomas, yes, way cool. Gaurav, they are linked actually, yes. So an outpost is deployed in your data center, but it is controlled through one of the regions. It essentially looks like another availability zone in a region. Yeah, so it's pretty cool. All right, now, a couple of questions or discussion. When choosing an AWS region for your services, data, and applications, why do you want proximity to your customers? Why would you want that? What's the primary reason? Latency. There you go. That's it. Entirely latency. Yep. Faster results, customer experience. Yep. All right. Quick review then. All right. So we look at Sao Paulo. We already said that Sao Paulo is down in Brazil. It's our most expensive. Oh, wrong one. It's our most expensive region, and it currently has 3 availability zones. Now, obviously, we only have one region in South America. In fact, according to that map, we don't have any others planned. No, we don't. But we do have customers in other locations in South America. So we have other edge locations out there as well. All right, so our customers can interact, up here, and their data is being dragged from the Sao Paulo region. Now, again, if your goal is to be global and you've got South American customers, would you put your origin data in Sao Paulo? Why not? Exactly, cost. The CDN is taking care of our latency concerns, but Sao Paulo is not taking care of our cost concerns. Yep, I'm going to put that. I can put it anywhere because I'm using a CDN to distribute my content. All right. All of these cool services and all these cool regions and stuff. Actually, you know what? I'm going to go back one. I'm going to go back one. And I'm going to take us back to the Outpost page. I'm going to tell you something else that we have done with Outposts. It's not part of the course, but you're all cool people. Regulation. So it was in there for operating with the Brazilian government, Brazilian entities. They have sovereignty rules. Actually, that's why a lot of our deployments happened. The Frankfurt region was created for exactly the same reason. I'm going to go back to Outposts, and so if we look at Outposts, remember what Outposts are. Outposts are AWS infrastructure put somewhere else. All right. Now, I'm going to tell you about some other things that were on the infrastructure page that you may have noticed that are not mentioned in this course, but I'm going to tell you what they are now. Local zones. Right now we have 17. We have another 34 coming. Now, essentially what a local zone is we've taken Outposts and we have deployed it to a city where we do not have AWS infrastructure. So let's click on, no, I don't want that one. I want, where's it gone? Why won't you let me click on it? Okay. No, all right, don't worry. Okay, so we've got Northern California, we've got Oregon, and we've got the GovCloud. But we have customers in LA, and I apologize if I'm pointing to the wrong part. We have customers in LA that need ultra low latency calculations on seismic data. Okay, they're very worried about the big one, as everyone on the West Coast is. And plus, they've got about another 50 fault lines all converging around there. Now, even sending the data to Northern California or Oregon introduces unacceptable latency. So they came to us and said, we want low latency access to compute. Give us some. So we scratched our heads, the boffins in AWS, and go, oh no, we'll put AWS where you are. And so we've taken this concept of Outposts and we've put a whole bunch of AWS infrastructure in Los Angeles, and these are called local zones. So in exactly the same way as it would be on-prem for you, it looks like, it looks like it's managed from Oregon, which they are. So the Los Angeles local zone is managed from Oregon, but the physical infrastructure is in Los Angeles. So now our seismic data customers get ultra low latency access to compute, but it's just happened to be managed from Oregon. And so that's what a local zone is. It's kind of like an outpost that we manage and have deployed in various locations. Right now we have, I'm trying to remember them all. Can I click on it? No, it's not going to let me click on it. No. Anyway, so we have 17 Brazilian government requirements for local storage. Yeah, exactly. So that's what a local zone is. It's like a AWS Lite put off into metropolitan areas. Can an outpost be in Monaco if Monaco Gov? I guess they could. Yeah, I don't suppose there's any reason why the Monaco government could not deploy outposts. Yeah, totally.
And so Stuart, you sort of build outposts on customer demand. If somebody's willing to foot the bill, you'll build it.
If somebody is willing to pay for AWS resources, and so we don't charge you any extra to use use a local zone. No, but we have to have customer demand for that location. Yeah, it's got to be worth our while to deploy it. Yeah. Outposts are different. As long as you want to pay the outpost bill, then we'll,
Yep.
yeah. But yeah, pretty cool, huh? All right, next one that's really cool. Can't spend too much time on these, but the other one is wavelength zones. Wavelength zones. Oh, my son's just come in. You want to say hello? Oh, yes, please. Yeah. A wavelength zone is, again, it's working on the outpost concept, but now I need a white screen again for this one. Quick white screen. I'll do this one super quick because we're just getting up for lunchtime. All right, here's my cell phone, right? And it talks to the cell phone tower. Beep, 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 like that, which then routes the information from the cell tower down to the telco's data center, which then traverses the public internet to access a web server that is running, let's say, on AWS or any other cloud provider. All right, so we've got lots of hops here, and there are many hops in between on this. I'm just very much simplifying it. Now, the whole idea behind wavelength is we put an outpost here, or outpost. We've got AWS infrastructure there. So now your cell phone goes direct to the telco's data center, and we cut out the public internet. So companies can now choose to deploy their workloads to wavelength zones, which give ultra low latency access from mobile devices. It's picking up a lot of speed, I will tell you that. So currently 24 wavelength zones, and there are a lot more announced as well, but we're just not showing them here. Anyway, pretty cool, right? Right, now, there we go. So that's our outpost. There's our global infrastructure. All right, all of these regions are wholly self-contained, all right? I've just told you, none of your data will move out of a region unless you explicitly tell us to do so. That does mean, though, that you don't interact with AWS, you interact with AWS in a region. How do you do that? Well, we've got one of them we've already seen, the AWS Management Console. So I'll bring my AWS Management Console back into, which I think I've closed it. Give me one sec. Unless I've got it. Oh, no, it's still there. All right, it's here. So if we look up here on my browser, we see North Virginia. Here are all of the regions that I have access to. So you can see I'm in North Virginia. If I now go to instances and I go and create an instance, it will be created in the region displayed here. All right. So yeah, I'm not going to launch an instance, but it will be located in this region. I can also switch regions and go and see the other resources, but each region is completely independent from each other. All right. So that's one way to interact with AWS services. Oh, I've got an alert. Oh no, that's right. I know what that one is. We also, this is a really cool one. I've been working with AWS for a long time, and I only discovered this like a year ago. Quite often we want to do command line based stuff to interact with our infrastructure. And the same is true in the cloud as it was on-prem. This one is called Cloud Shell. Now, hopefully it's going to launch pretty quickly. And essentially, it means we don't have to deploy Bastion hosts. All right. As long as you can connect to the AWS Management Console, you can now have a shell fully configured, monitored, and audited. I think, if I remember correct, oh no, it's a different service. All right. So now I don't have to manage my Bastion, my Bastion infrastructure, right? I have to be authenticated to get into the AWS Management Console. Within hopefully about 30 seconds, I have an interactive shell, like a bash shell, and it saves my home directory. So if I want to put my scripts up there, and templates and whatever, I can leave them on there, and it turns itself off after, I think it's 15 minutes of inactivity. Then I come to work the next day, I click on the Cloud Shell, and I get an interactive shell with no Bastion hosts, no SSH keys to manage, all that kind of stuff. And it doesn't listen on the internet. Right? We do not have to have a Bastion host on the internet. It's just there. It's normally a little bit quicker than this. Come on, browser. There we go. I'm in. There we go. So what was that? 30, 45 seconds. And now I've got that. So I can do AWS S3, LS. There you go. There's all my buckets within my account. Just like that. And if I save my script, save my whatever in my home directory, I don't think I actually have anything in this one. Oh, I do. Hello.txt. I touched that just to prove that it was there a while ago. 8th of March was the last time I did that. So Cloud Shell is pretty cool. All right, other things. Services. If you click the services button, you get groups of services where we've logically grouped them together. So if you want to look at our database offerings, click on database, and then you'll see. So you'll see these ones. We'll be doing a couple of these in the course. I like this one. Quantum computing. You want access to a D-Wave quantum computer? Off you go, Amazon bracket. Ready for the next cool one? You want to launch a satellite and control it? Go. AWS ground station. And we ain't going to launch, I guess technically we could eventually with Blue Horizons, but right now you have to take care of launching the satellite. But we have, if I remember correctly, 13 ground stations where you can control it. And the cool thing, we have such massive data processing. Thank you very much. Thank you. My youngest has brought my lunch. So that kind of tells you we're going for lunch fairly soon. Yeah, so obviously we have a lot of compute available in AWS. We have unlimited storage with S3. We've got machine learning, artificial intelligence, programmed ETL pipelines, analytics, all in the cloud ready to go. So if you want to draw down your data in a stream or in batches from your satellite, you now don't have to transfer it over the internet. You just suck it straight down into AWS and start processing it. And if you've got a real-time feed, you're processing real-time in the cloud through your satellite. Isn't that cool? Anyway, so that's ground station. Somebody's going to ask.
Yeah, I'm assuming that service is consumed by the U.S. Department of Defense. That's what they use.
I couldn't tell you actually. I mean, if it was there, I'd tell you. I'm just trying to see if there's use cases on it. Sometimes we'll have contact. No, maybe we're not. No. Yeah. So this is one of those where you actually have to phone them up and say, I want to control my satellite. I can neither confirm nor deny. Yeah, I like that. And you know what, Leonard? It is amazing, isn't it? It could be DoD. Yeah, it could be private companies. You know, it's relatively cheap to launch your own satellites these days. So, I guess we've got enough demand to launch 13, 13 ground stations. So yeah, it's pretty cool. I love it. Right, so there's that one. I just like showing off the cool stuff. Yeah, click compute and see how many options you got. Compute, outposts, serverless, Beanstalk, EC2, batch processing, app runner, Lambda, all in there. AR and VR, augmented and virtual reality. Yes, we've got AWS Sumerian integration. And here's a really interesting one for, no, where's it gone? I lose things. Management and governance, very important. Look at all of these different services and offerings, all to do quantum compute. A lot of you. Yep, they do. Yep. All of these, all to do with governance and observability and compliance. All right. There's another one called AWS. It's not listed on there. Artifact. AWS Artifact. So if you need to download reports for an auditor for a particular compliance thing, you can do that through the Artifact service. All right, it's a free service. Sometimes you will have to sign an NDA to get access to the reports, but yeah, you do have access to the reports. Click View Reports, and let's say you want to do 27,000. Is that one in there? Yeah, there we go, 2017, whatever. You can select those and you can actually go and download. This one looks like we can actually download the report. There you go. There's the thing. I'm not going to open it. We're not going to have time to go through it. But that stuff is available to you if you are going through an audit. Loads of other things in here. We're just really scratching the surface. Machine learning. Look at this. All that machine learning and artificial intelligence. services. Loads. I think it's probably the biggest section now. It's a massive push on using that. Anywho, all right, so that's one way, the management console. The other way is through the CLI. Essentially, what I just showed you with the Cloud Shell, which should still be running. Should connect me direct in there. Yep. You obviously can do this through your console as well. So if you get API keys, you use those, and basically you can manage your complete infrastructure through the AWS CLI. And if you're using AWS programmatically, so you're incorporating the services into your applications, we've got SDKs as well, which is pretty nifty. Now, the fact that I've just shown you the console does not mean I am endorsing the console for production work. All right. Anyone who's been in operations will know that while UIs are amazing for learning and visualizing, you do not do your production changes or even your QA changes, whatever, through the management console. You do automation, infrastructure as code, delivery pipelines, whatever. I love the management console, but don't ever use it for production changes. Great for dashboards. Humans love images, right? That's how we consume the vast majority of our information. So the fact that we can create these dashboards is fabulous, but don't make changes through the management console. There you go. That's my caveat. Okay, back to here. All right, so we've done those. We've done the demo, and we've done those other interaction pieces. All right, quick knowledge check, and then we're out to lunch. Everyone ready? Which of the following is true for global infrastructure? You read and pick. What do you think? D, that is correct. Well done. Region consists of 2 or more availability zones. Next one, which factors should be considered when selecting a region? Select any 2. Are we straight in there? B-A, A, yeah. Yep, everyone got it correct. Proximity for latency and governance is your first filter. Which statement best describes CloudFront? Yep, you're in content delivery network. Which site does Amazon CloudFront use to cache copies for content for faster delivery to end users at any location? Yeah, you all got it straight out of the edge. Which actions can you perform with outposts? What does Outpost do for us? Yep, everyone's in there. Awesome. All right, that is it for module 3. Let's take lunch. We're going to do 45 minutes. So let's be back at, what is it, 12:15. Let's be back at 1 p.m. your time. So 1 p.m. Go grab some lunch. Go caffeinate yourself. Yes, I am sharing slides. Thank you. I will be doing that over lunch. Yes. Excuse me. All right, go have some lunch. Go hug your loved ones and then come back raring to go. Where is my mouse? Yep, I can do that. There's my mouse. Oh. Sorry, my mouse has just, I've been having tech troubles since lunchtime. There's my mouse. Okay, got it. All right. So we had the region, we had the availability zones, we had the logical container that you created, which is a VPC. And then inside a VPC and an availability zone, we had subnets. So it was, yeah, in the middle box. Yeah, the middle box is the VPC that you create. Remember, it's not a real thing. It's just a logical container where you put your IP-based stuff. We're coming on to public and private right now. VPC is in no, you have the choice. And so subnets, we'll say right now we've got one public and one private. The difference between the two is whether or not a host in here can get a public IP address. Sorry, I've done it the wrong way around. I do apologize. This is public, isn't it? So when I provision my my EC2 instance in a public subnet, I have the option to give it a public IP address. In a private subnet, I do not have the option to give it a public IP address. That's the only difference between a public and a private subnet. Now, there are a few things missing from here that we're going to put on right now. Oh, we're going to add to as we go. So, subnets. Subnet is a section of a VPC. Could you repeat? Of course. So, a public subnet, right? This is essentially the drawing I just did. A public subnet, when I deploy an EC2 instance, I have the option to supply it with one public IP address. That really means it can accept incoming traffic from the internet. In a private subnet, I do not have the option to assign it a public IP address. So anything in a private subnet cannot accept incoming internet traffic. That's the difference between the two. Is one setting which says enable public IP, yes or no. Okay. All right. On to a little bit more of our diagram. Although you have the capability of accepting incoming traffic on this web server, it still can't do it because it has no device to move the traffic into and out of the internet. And that's where we have this thing called an internet gateway. So what we do, we create our VPC, we create our subnets, we add in our hosts, and when we want to enable traffic to and from the internet, we create an internet gateway and we attach it to our VPC as shown here. Now, it's not a single device, it's not a, it's not a single point of failure or anything like that. But this is the bit that allows traffic to go out of our public subnet to the internet and allows inbound traffic from the internet to go to those hosts. So remember I said that this server could be given a public IP address. In reality, that public IP address exists on here, on the internet gateway. All right. So that's the IP address. The outside world sends its traffic to the internet gateway, and the internet gateway sends it to your public, to your EC2 instance in the public subnet. Now, a couple of other things that we can attach. So does that make sense? Don't worry about privates. We'll come on to, we'll clarify privates in just a second. All right, so you still have to make the choice, though, of when you deploy a host in here, it will get a private IP address, from the subnet. You remember the drawing I did? Yeah. Aha. If you could, Gaurav, ask your questions publicly, then everyone gets the benefit of the question and the answer. But yeah, how can how can they be differentiated? Right, we'll come on to that. Okay, so this is a public subnet. you have the option to attach that public IP address, but remember the IP address is attached here and we direct traffic that way. So that is a public subnet. Other things that we can attach to our VPC, we have another one called a virtual private gateway. A virtual private gateway allows you to create a private connection over a VPN tunnel from somewhere outside to your VPC. So a common one for this will be your corporate data center. The downside of this one is that you are using the public internet. So using a software VPN, even though I know we're running hardware here and hardware here, but it is a software VPN because it's going over the public internet. But it's great for administration traffic, low-level application traffic, that kind of stuff. So this is one of the ways that we can create our hybrid networking is we attach a VPG, virtual private gateway, to the VPC. Here we go, acronym hell, and then traffic flows once we've configured your router. So this we call this a customer gateway. This is your router, your firewall device, your VPN device, whatever it happens to be. We link them up, and then based on routing rules, content in here can go over there and it can go back. Again, it does very much depend on your routing rules. So that's one way of wiring up our corporate data center to a VPC. Now, a couple of things to note. This is obviously running over the public internet, and by IPsec design, this is not an AWS limitation, you are limited to 1.25 gigabits per second. That's a protocol limit, it's not an AWS limit. Okay, so still quite high bandwidth, but it is going over the public internet. If you want a more private connection, I've just realized there's a slide missing for public and private. Don't worry, I'll sort that one out. The other way we have is a direct connect. We'll go back to subnets and clarify that in just a second. Direct connect. So direct connect then is a leased line. It's a physical connection between you and AWS. And there's two ways to achieve this connection. One of them, if you are lucky enough to be in a data center that AWS is physically present in, you can connect your router to directly into AWS. AWS then makes a logical connection to your virtual private gateway into your networking, right? So we've got a completely private line through AWS to your assets in AWS, all right? If you are not lucky enough to be in a data center that AWS is, you go through a partner. And so they have gone through the expense of creating a physical connection between the partner and AWS, and you connect to the partner. All right. So you've got choices. You either go direct like that, or you go through a partner and go in. But either way, you're routing your traffic over a private connection, wholly owned by you. So it's predictable on cost and latency and performance. And all of the routing is controlled by you at either end, typically using BGP. Can you connect through AWS Outpost? So as I understand it, I've not used Outpost. Outpost would be over here, and it uses VPGs to connect you back up there. However, take that one with a pinch of salt because I've not really done any AWS Outpost work. So I'm not sure, I'm not 100% sure of the back channel to link them up. But I can actually, I want to find that out, so I will find that out. Okay, so that's our direct connect. We take care of the routing here, so we have full control of the routing, how our corporate traffic goes over the line and is then distributed internally to can BBC. Okay, this is a great one. And this, I can tell you're a networker, right? No, you can't have overlapping IP address spaces. No. If you are a company like you of sufficient size where you're going to be joining your corporate to AWS, get your networking team involved. they'll figure it out for you, and B, you won't get told off for doing networking without the networking team. So what they will do is that typically a networking team in running corporate data centers, they have their IP ranges, and they know that, you know, VLAN 1 is databases, you know, and I've got another data center over there, and all the IP management is done by your networking team. Typically, they need to be involved, so when you're creating your IP spaces in here, they don't overlap, because you cannot route overlapping IP addresses with AWS infrastructure. It doesn't work. If you want to do seriously complicated source natting and denatting with software routers, you can do that. I highly don't recommend it. But yeah, so plan your IP space if you're doing these kind of hybrid networks. And absolutely involve your network team. Trust me, it's going to save you a lot of time and trouble. Okay, so that's our 2 ways of connecting in. All right, so we've got direct, oh, sorry. Yeah, we've got our direct connect, let's clear that, which is our lease line. We also have software VPNs running over virtual private gateways. Now, I've got to go and clean up something because it looks like there's a slide missing for some reason. All right, subnets, public and private. Remember I said an IP address, sorry, a host in a public subnet can have an IP address, and it gains access to the internet through the internet gateway. But what if we have a private subnet here, and that's got some logic servers in there, business logic servers in there? The internet gateway allows egress and ingress. But how does a private traffic get out to the internet? Well, we do that with a NAT gateway. Now, a NAT gateway sits in here, has a leg there, and has a leg in there. All right. So all of your hosts here will have a default gateway set to the NAT gateway. The NAT gateway will then send it out over the internet. Okay. However, this NAT gateway cannot accept incoming NAT, network address translation. Yeah. NAT, N-A-T. Again, this is more for the tried and trusted networkers. But yeah, so it's a address translation. Right, best way to think of it, you've got a cable router at home, right? And you've got 5, 10, whatever devices. Not all of those appear on the internet. What appears on the internet is your cable router. It's exactly the same, all right? So all of the traffic coming out of this private subnet appears to be coming through or from the NAT gateway, network address translation. I'm saying that this IP address appears as this IP address as it goes out, and this one, and this one. IP masquerading NAT gateways, again, it's a bit of a, the networkers will get it. If you're not involved in networking, don't worry too much about it. Just letting you know that there is NATing options, and that's how you get private traffic out to the internet. But you can't send traffic into a NAT, right? It's a NAT gateway, not a two-way NAT gateway. So all the non-networkers are going, what the heck is he talking about? And all the networkers are going, oh, cool. Anyway. All right. So that's our connection options. Let's do our best, see what we can do. So isolate databases containing customer personal information. Where would you put databases? Even if you're a non-networker, we should be getting this. Yep. That's it. B. Yeah, we're going to put that in a private subnet. A VPN connection between a VPC and your corporate network. Where do you terminate that connection? So, yep, that is C. For some reason, my script, I'm having serious internal networking problems now. Oh, lost my mouse, lost one of the screen. No, whatever, let's just carry on. Support a customer-facing website. I've lost a screen. Right, just give me one moment to get my screen back. Distinct resolution. All right, almost there. Okay, that one's up there. Okay. You are correct. It was C. Next one. Oh, I've given you the answer. Look at that. Support a customer-facing website. A bit of a interesting one, this one. Yes, technically the answer is A, but in reality, the answer is also B. So if I go back to this diagram, I would also put application servers in a private subnet because our elastic load balancers, remember we talked about ELBs, they will be in the public subnet. And that means we get to keep our web server and application servers in a private subnet, keep them private and off the internet as well. Anyway, so that's, yeah, technically that is the correct answer, but it's also not the correct answer. And the last one, can we tell, establish a dedicated connection between on-prem and a VPC? Obviously, yeah, the answer is D. Okay, hopefully my system has settled down a bit now. It was weird. I've been running it hard this last week. So sort of, yeah, the external side of the NAT gateway lives in the public, and the internal side of the NAT gateway actually is so really it's actually a routing rule. I don't want to get too technical, but it's a routing rule, not an interface. Yeah. If you are more interested, absolutely come on the Architecting on AWS course, and we talk about this stuff in a lot more depth. Mouse, come on, mouse. There we go. All right. So far we've talked about IP networking and how we carve up subnets and the fact that we do put hosts in those subnets, but we need to keep those hosts safe, don't we? For that, we have two control mechanisms. We have NACLs, and security groups, and they operate in different parts of our network. Okay, so traffic comes in from the internet, right? And it hits our internet gateway, which then, oh, sorry, I put it in the wrong place, which hits our internet gateway, which then goes through a routing table. I'm not going to talk about routing tables in this one. When the routing table then says, okay, that piece of traffic needs to go over to the public subnet, it's going to hit the subnet boundary, right, the edge of the subnet. And then we're going to inspect that traffic, okay? We're going to look at it and say, and make a decision, is it allowed into the subnet or is it allowed out of the subnet? And to do that, we use a NACL, right, Network Access Control List. Assuming it's allowed through the NACL, it then goes on to be filtered by a security group, which is a firewall for an EC2 instance. All right, so let's follow those packets through. First of all, it touches the internet gateway, which then gets filtered through a network access control list. The network access control list lets it into the subnet or not, and then it talks to the security group, which allows it through or not before it touches your EC2 instance. So a network access control list then is a stateless packet filter. It works down on layer 4, and excuse me, most people don't touch these, right? They are left wide open most of the time. They are stateless, a bit more difficult to program because for every inbound rule, you must have a corresponding outbound rule. Otherwise, the packets get in and they don't get back out again. Most people leave them wide open because we usually control everything through security groups, which are coming up in just a second. But they're there for high compliance, high security, and you can use them if you want to. So default is allow all, and you can do custom ACLs to deny all and then put your allow list in there as well. So yeah, that's down layer 4 at the subnet boundary. Once the packet is in the subnet, yes, it could restrict IPs, yes, and IP ranges and particular hosts. Yes, absolutely. Yeah. Like North Korea. Yeah, totally. However, we can do that further out on our network as well with things called WAF, like web application firewalls and things like that. But yes, you can certainly do country blocks on it. Yeah. As long as you know the ranges, you can certainly do it. Yeah, so that's your inbound traffic. Once traffic is inside the subnet, it doesn't play any part anymore. So if you're talking host to host communications inside this subnet, NACLs don't work anymore, right? They only control at the boundary. And like it said, it's stateless. Okay, we've got some funny diagrams for this, but basically, as the packet comes in, it gets inspected, and as the packet goes out, it's inspected as well. But you need a corresponding rule for both directions, so that's stateless packet filter at the subnet boundary. Like I said, once it's in the subnet boundary, you're then subject to security groups. Security group is a firewall that protects an EC2 instance. Okay, so this is also an IP packet filter, but now it's protecting a particular particular instance, and this one is stateful. The difference with this one is all outbound is allowed, all inbound is denied by default. And then so you would program, let's say you're listening on HTTPS traffic, so you would open up port 443 to the internet. Okay, no problem there. If we were doing NACL programming, I would need to allow inbound to port 443, and I would need to allow outbound from port 443. But generally, like I said, we generally don't do that. We do it here at the security group level. So at the security group level, I will allow inbound 443, and it does connection tracking. So as a packet comes in from the internet, it tracks it and will allow the outbound packets to go back out to the internet. So that really is the difference between the two. Well, there's two main differences. NACLs operate at the subnet boundary and are stateless. Security groups operate at the host level and are stateful. Now, there is another layer on here that you have the option to use inside your operating system. You can use an operating system firewall as well. So, you know, Windows firewall, IP tables for Linux, you know, whatever it happens to be. Can you please, stateless? Yes. Okay, so we'll go stateless is as the packet comes into the subnet, we just evaluate it. Can it come in? Yes or no? A return packet from a web server to a browser is still a packet that is exiting your subnet. So for NACLs, you must have a rule that says your traffic can go out. So there's no connection tracking. All right, so you need to allow in. So you need a card to get in and you need a card to get out. With a security group, you just need a card to get in and you're automatically allowed back out again. That's the difference between the two. Cool. All right, that's our stateful packet filters. Oh, we've done, oh yeah, so there's our traffic flow. This is our complete traffic flow for now. So we've got a packet, hits the internet gateway, is evaluated for the inbound by the network control access list, is evaluated by the security group. If it's allowed in, it's automatically allowed out, but it is inspected through the network access control list on the way out. All right. So you tell me, how did I explain that okay? What is the difference between a NACL and a security group? First of all, where do they apply? Let's break it down. Where does a NACL apply? Where does a security group apply? Yep, subnet boundary for a NACL. In a little while. Security group as at the EC2 instance. Yes, that is correct. That was my number 2 son. Come to say hello. Yes, that is correct. All right, next one. What about the stateness of them? Which one is stateful? Which one is stateless? Yep, NACL is stateless. Correct. So therefore, security groups are stateful. Correct. All right, so we got those. Yep, network NACLs are virtual firewalls for subnets. They do stateless. Security groups are virtual firewalls for EC2 instances and are stateful. Awesome. Excuse me. Okay. Hands up, who remembers the IP address for www.amazon.com? No, no hands. Humans are not very good at remembering numbers. Not that amount of numbers anyway. We work on names. It was really easy for me to remember www.amazon.com, but I've got no chance of remembering the numbers because the computers work on numbers, they don't work on names. So to do that translation, we have AWS Route 53, which is a DNS system, right? You type into your browser, www.amazon.com. Your computer has no idea what that means because it's a computer, it works on numbers. So then it asks this thing called a DNS resolver, which says, do you know the IP address for www.amazon.com? And they go, yeah, I do. And so it gives it back, and your browser then sends the packets off over the internet to there. That essentially is how DNS works. All right. I think it's the biggest distributed database on the planet. But let's not get into the technicalities. Its job is to give you an IP address for a particular website. That's essentially what it's for. I'm going to close my door, so there's a lot of noise upstairs. 1 second. All right. So we have, Amazon is part of the big global DNS system. We have many thousands of servers out there. If you do security operations on AWS, we go into this in much more detail as well. So this is what Route 53 does. Excuse me. Route 53, you can programmatically control your domains. If you've got a personal domain through GoDaddy or name servers or 123 DNS or whatever it happens to be, you can go onto the web page and put different rules in there, different names and IP addresses. We can do that programmatically through Route 53. So as you're deploying new stuff through your automation, you can automatically update and change your DNS records as well. So yes, what does Route 53 do? Routes users to your internet applications. Connect users from outside to your inside systems and manage your DNS records. Route 53 is also a registrar, so you can purchase your domains and fully manage them all within AWS as well. So that's pretty cool. So it's a full domain registrar. And it works very tightly with our other systems. So it's fully API driven if you want it to be. Yes, we can do it through the management console, but you can also program it through automation, through scripting, SDKs, whatever it happens to be. So we can do it all programmatically. Now, Route 53 is one of the mechanisms that CloudFront uses. Remember, CloudFront is our content distribution network. Now, we've got 320 plus remote locations in our content distribution network. And what we can't do is tell all of our clients what those 310 IP addresses, because there's probably thousands of them. So we actually use Route 53 to do that, and we can program Route 53 to respond in a certain way. So for example, we've turned on a CloudFront distribution network. My origin is in West Virginia, and our customer is in Tokyo. When my customer in Tokyo types in www.example.com, we want that to be location specific. So the request comes into Route 53. Route 53 says, oh, this is a CloudFront distribution. Oh, and I can tell where they are. I can tell where they are by source IP address and lots of other various reasons. But basically, it detects where the client is, and it says, I know, we're going to send them to the CloudFront endpoint that is closest to them. So they work together, okay? And that's how the two of them tie together. Now, it could be that your origin is some web servers, whatever it happens to be. But yeah, so that's essentially how the two work together. Route 53 is an intelligent DNS system. It's not just dumb. You put your records in and it gives out answers. We can actually program in intelligence on this. So we've got geolocation. Where is my client located? We've got geoproximity, which says if they're within this area, then we can send them here or here. We can do multi-record responses. So if I've got my application deployed in region 1 and region 2, I can do active-active. So I can tell Route 53 to return these record sets. Or I can do active-passive. So it can do health checks as well. So I can say this is my primary site and this is my secondary site. And if this one goes wrong, automatically change the records that you return to customers to this one over here. And we can do weighting as another one. I could put 90% over here and 10% over here. So I've got like a pilot light system that's just running at low capacity until we do a failover. So we have a lot of options with Route 53. It's a pretty cool service. All right, hopefully on this knowledge check, we're not going to get too stumped with networking stuff. Any non-networkers a bit what has he just talked about? Probably. Any networkers going, yeah, that all makes perfect sense. What do we got? We've probably got a mix of the two, right? Yeah. All right. Not a networker. Not a networker, but does it make sense at a higher level? Maybe not the details. Good. Think so. Good. Excellent. All right, let's have a knowledge check. Which component or service can be used to establish a private, dedicated connection between a data center and AWS? Oh, Mary's got to make sense. Thank you. C, direct connect, correct. Which statement describes security groups? I'm not going to read through them. You tell me. Okay, the Bs have this one, and we did get 1A. So by default, they do not allow inbound traffic. Okay, you have to stateless and deny all. So that doesn't apply to either. So stateless would be a NACL, but NACLs allow all by default. Okay. Which component is used to connect a VPC to the internet? Yep, you all got it. Internet gateway. Which service is used to manage the DNS records for domain names? Yeah, everyone's straight in on that one. Almost. DNS records is all Route 53. So to be a little bit nerdy, it's a play on Route 66 and DNS works on port 53. There you go. We're a little bit nerdy there. Okay, I think this is the last question. Which statement describes DNS resolution? Anybody remember the point of DNS? Yep, D translates domain names to IP addresses. So human to computer. All right, that's it. Let's take a quick break before we move on to the next module. Let's take 5. So let's be back at 1:50, and then we'll crack on. Yep, no worries, Gaurav. I'll do that right now. If you could just paste me in your email address, I kind of lost it when my screen went a bit funky. Then I'll get those off to you now. Thank you. All right, back again. Sorry about that. The plumber turned up. Gaurav, did you get the email? You should have. You did. All right. Has anybody else not got their slides? Need to create an account. Yeah, that's normal. All right, looks like everybody has got their slides. Okay, that's good. All right. Let's get this show on the road. Oh, you did not get yours. Okay, if you could send me your email address, Div, I'll get that done right this second. You could just, that's it. Give me 1 second. I'll get this out to you. No, it's not an attachment. No, it's a link to Gilmore. No, it's not an attachment. All right, Div, yours is on its way to you right now. No, it's not. Hold on. Yeah. Invalid email address. Oh, I see. You put a dot in there. 1 second. Jerry, does that mean you didn't get them? You didn't. Okay, let's get you going now. Okay, Jerry, yours are on the way also. Gaurav, you have to use the redeem code that's in the email. Yeah, so you have to create your account and then use the redemption code. All right, so let's move on. Okay, assuming my system is going to hold up for the rest of the day. It looks like it.
Hi, Stuart. This is Gaurav. There is
Hello.
no redemption code. There is order number and license code.
Yep,
Which one?
license code. That's the one. Yep.
Thanks.
Yeah, no worries. Okay. Storage and databases. Remember, part of the fundamental deployment of anything is compute, network, storage, databases. So let's look at those two right now. Storage and databases. What are we going to look at in this one? Let's grab my pen. There we go. They're going to work. Oh, it looks like it might work straight away. Basic concepts. Yeah, we're going to do that. Then we'll look at EBS. This is your hard drives for your EC2 instances. S3 is our object store. This is our unlimited object storage in the cloud. EFS is our shared file system. We'll look at a couple of the other ones. So we'll summarize all of these together. And then we're going to move on to databases. So RDS is our relational, so transactional databases. And then we'll have a real quick look at DynamoDB, which is a NoSQL key value store, and then a quick summary at the end. Okay. Storage. There are 3 types of storage, and we'll look at the main service for each one of these. Block storage. Block storage is the hard drives that go in your EC2 instances. All right, so they're called block devices because the operating system carves up the media into blocks and then writes files to them. Okay, these are designed for random access, for being efficient at storing, excuse me, at storing files inside an operating system. Typically, they have a file system on them, NTFS, UFS, ext4, UFS, all different sorts. But really what they're doing is cataloging and efficiently storing data on your disks, your physical medium, your hard drives, your rotational media, your SSD drives, your flash drives, any of those. That's all block devices. But they're all local to the machine they're attached to. That's their key thing. Going to go up the stack now. File storage. This is your Y drive or your Z drive on your network. Or if you're in the Unix world, this is an NFS mount point. So file storage is for sharing files at the network layer, but they still operate as block storage, but they are just accessed over the network instead of being plugged into the motherboard. And the last one, object storage. This is where we operate at the whole file level. This one does operate over the network, but it uses a layer 7 protocol. Like we're using HTTP puts and gets. And so this one works as the whole file level, right? So there's no chunking it up into small bits to efficiently store it onto local media because there is no local media. All right, you put it to a storage service on the internet, and that service takes care of storing it and replicating it and protecting it behind the scenes. So kind of going up the stack. So we've got local storage, we've got network storage, and then we've got internet storage. And that's probably the best way to think of them. So let's real quick summarize them. Yeah, block storage. Files are into equal size chunks on physical medium. And that is how we store our data and operating system on an EC2 instance, right? You cannot have an EC2 instance without without a block store, somewhere to write the operating system to. That's our block store. That block store is provided through the service called EBS. We'll come on to that next. There is another way you can get additional storage on your EC2 instance, and that one is called instance storage. Now, I need to explain this one quite carefully. This is a physical AWS server. Okay, this is an AWS hypervisor. It's running your virtual machine. In that server is local disk, high-speed, very high-performant SSD drives. And what we can do is give your EC2 access a portion of it. Okay, so you have access over the local PCI bus, so you've got very low latency, high IOPS. Now, this sounds really cool because I've got super fast disk access. Now, the thing is though, remember this is on the local physical server. And if you turn off or terminate for some reason, your EC2 instance goes offline, you lose anything inside the data store. So while it's very fast and high speed, low latency, high IOPS, it is really designed for scratch space, working space, downloading data and crunching it quickly. All right. It is a non-persistent, ephemeral data store. Okay. If you stop it, if you terminate it, whatever, then essentially that instance store disappears, which is cool. Like, know its use case and then you can use it effectively. Now, if you want persistent storage, if you want your operating system, bigger system drives, that kind of stuff, then we use EBS. EBS stands for Elastic Block Store. An Elastic Block Store, remember I said a block device is a hard drive that we put a file system on that chunks up data. Well, EBS actually works over the internet. Sorry, not on the internet. Don't say internet. It works over the network. Now, again, we have a physical AWS server here, and somewhere over here, we have the EBS service that gives you a portion of storage, which is then attached to the AWS physical server over the network, and we present that to your instance as if it was a local hard drive. Now, the key takeaway here is that your instance and your storage are decoupled. So what that means is I can terminate this EC2 instance or shut it down, and not terminate, but turn it off, basically pull the power out. but the EBS volume persists. So I've got the data, which means that I can attach it again and start it up in exactly the same state that I left it. So think about this one is almost is like an external SSD drive. All right. When you close your laptop, you pull away your external hard drive and all your data is still on it. Okay. That's really the difference between the two. You cannot, so let's go back one. You cannot use an instance store as the operating system disk, right? It cannot be where your Windows is in your C drive. You would add an instance store as a D drive if you're in Windows, or an additional mount point if you're in the Unix world, right? So it can't be. But when you're talking EBS volumes, your root drive, your slash or your C drive must be an EBS volume, and you can add additional data drives as well. So I think you can have up to 16 EBS volumes attached. So you can get a lot of data, high performance data attached to your EC2 instance. Sorry, got a dry throat coming. Okay, so that's our EBS volumes. Essentially, if you're used to working, you can think of it like a SAN, all right? Best way to think of it if it's not quite syncing yet. EBS volumes are like a SAN. All right, remember your SAN would be attached to your VMware. Your VMware would attach to the LUN and present that LUN to your EC2 instance. You don't have EC2 instances, to your VMware virtual machines. All right, and it appears like a local drive. Same kind of model. Technology is completely different, but the model is the same. Now, one of the things we do, or we can do with the EBS snapshot, with an EBS volume, is snapshot it. Okay, so that means we can basically take a block by block copy of the disk. All right, it's done online. Best practice is they call it quiesce the file system. So we can essentially freeze the file system till we get a full point in time recovery point, but it can be done without quiescing the file system. Once we use normal backup routines for this one, so you got incrementals and differentials, right? So in day one, you do a full backup, and then we do a block check. We only backup on snapshots the differences after that until you next take a full backup. All right. So you're not, if you want to take a backup let's say every 4 hours, you're not storing, let's say this is a 10 gigabyte file. You're not storing 10 gigabytes of backups every 4 hours. You're taking one backup at a point in time, and then you're only storing the incrementals or the differentials, that would be, sorry, the differentials from that point until you choose to take another full backup. Good thing about the EBS snapshots, obviously we've got them as part of our backup routine, but also we can use them as part of our DR routine. That EBS snapshot that we've just taken, we can turn that into an EC2 instance, an AMI. It's called an AMI. And so we can run another web server from the web server that we snapshotted as part of our backup routine. So backup and DR can use EBS snapshots. Now, another cool thing is that these snapshots, we can tell them to go to a different region. So if I've got cross-region DR, that's part of my requirements, I do my snapshots, and then I copy it over to this other region so that in the event of a failure, I boot my machines off of that copied over block device. Okay. So yeah, that's your EBS volumes. They come in various performance metrics. We're not really going to go into them in this one. Regions or A. So that would be regions. Yeah, it would be copied to a different region. Yeah. What was the other thing I was going to say? No, that was it. Oh, they come in different performance metrics. So we've got, so our EBS volumes, we've got, I'll do them real quick. We've got GP2, I think is the current version, multi-way region. Yes, it is. It is because you have to pay transfer costs as well. However, Sometimes your backup policy is the cost of doing business. But yeah, multi-way copying is more expensive than multi-availability zone, or just doing in-region backups. Yes. Yeah. Right, GP2, general purpose. Then if for high performance SSD drives, we've got IO2 drives. So they run into the tens of thousands of IOPS per second. That's your SSD drives. We then got ST1, which is magnetic drives. Though it looks more like a mushroom, sorry about that. Your magnetic drives are good for log processing, sequential access. Spinning hard drives are great for sequential access, but they're terrible for random I/O. So they're no good for running databases, but log processing, video processing, streaming, they're good for that. And then we have another one, which is a lower cost, SC1, which is, I think, storage cold one, I think it may mean. But it's still magnetic media. I'll try and make this one not look like a mushroom. There we go. Well, that looks even worse. That one just has lower performance. So it's lower cost, lower performance, used for maybe if you're running analytics, you know, every couple of weeks or something. So you don't want to pay a lot for storage, but you need sequential access when you need it. All right. Difference between the two, between an instance store and an EBS volume. What do we got? What's the difference? Oh, we had someone there. Who was that?
Yeah, sorry, that was my wife.
Oh,
So instance stores go away when your EC2 goes away.
correct. Yep,
EBS is persistent.
that's it. That's the big difference. Yeah. So Thomas, you have to contact me afterwards. We're going to charge your wife for listening in. You know, it's an additional seat. But just make sure she takes the test at the end. Okay. You know, I'm joking, right? Yes, you're right. Instant stores are temporary. EBS are retained. That's the word. Yeah. Okay, so that's our block storage. Now we've got object storage. Now this is a very seriously cool service, by the way. I'm going to tell you that up front. This is seriously cool. Object storage. We can think of objects, think about a file server, right? You dump a whole bunch of stuff on a file server. Think about the information there. We've got the name of the file. We've got the data in the file. And we've got things like size, date uploaded, change records, you know, stuff like that. Think about that. Now we apply that to an object store. Quite why we don't call them files, I don't know, but we don't. So when you're talking about an object store, primarily we're going to be talking about the S3 service. So simple storage service, simple again. Although behind the scenes it's anything but simple, but from your point of view, it's a simple HTTP interface. When you put a file on S3, the same things apply. Now we call an object, we call a file an object in S3. So we put that file up and it becomes an object in S3 because it has three constituent parts. It has the name, which we call the key. We have what's contained in the file, which is the data. And we have the data about the file, which is the metadata. So metadata would be upload time, MD5 hash, data size, you know, those kind of, that's pretty much it for system metadata. And the key is just the name. Pretty simple, right? That's what makes up an object. So carry that with us as we talk about the S3 storage, which is simple storage service. To store things in S3, you need what's known as a bucket. A bucket is just a logical container where you put your objects. All right, so it's just a logical container. A bucket in itself isn't really a real thing. It's just somewhere you put your things. Once you create a bucket, you have full control over access to the objects that you put in it. You also have full control over who can manipulate the bucket. So you have total control over everything to do with S3 and the data you put in it. We make it hard to make things public by accident in S3, right? We've all heard horror stories of agency this, company this, that have left their S3 bucket wide open and they've downloaded private data sets. And you know, those things have happened. I can also honestly tell you that every single one of those was a misconfiguration, not a service problem, okay? We intentionally now make it all buckets that you create, they're private by default, and we make it, is there an AWS tool to help data retention, auto length of time? Yes, there is. There is a tool called AWS Lifecycle Policies. Yes, so we can programmatically do that, yes. We'll go on to that real quick. So you have full control over the data in the bucket and the bucket. And we make it hard for you to make this stuff public. You can set a bucket to be public, and then you have to make each individual object in the bucket public, but none of that applies until you remove the global lock that says you can't have anything public. All right, so there's 3 layers you have to go to accidentally make a bucket public. All right, so don't do that. Keep everything private by default. And then when you're storing data in S3, you have various ways to pay for it. We call them here storage tiers, but really they're billing concepts, right? It's how you pay for and access your data. So let's look at that, because we all know that money is important. Well, I'm going to reveal them all. There we go. When you upload something, it goes into S3 standard. S3 standard is classed as hot data. So I like to think of it as, it's not done this way, but I like to think of it as this stuff is kept in RAM, all right? It's accessed really frequently. And we pay, hold on, let's get it the right way around. Hot equals dollars. Exactly. That's exactly it. But remember, everything in AWS is a spreadsheet operation. So we'll come on to whether it equals actual dollar or not. When you store something in S3 standard, you pay more to store it, but you pay less to access it. Okay? So yes, we're paying a premium because logically we're in RAM, but the idea is that you're going to access this, I don't know, thousands of times a second. And so you want to pay less for the access. You're okay paying a bit more to keep it hot, but you're going to pay less to do the access. So that's S3 standard. That is the default. It will just sit in there until you do something different with it. Your options on the do something different with it is this one, standard IA. Now I like to think of this one as now being flushed out of RAM and put on fast SSD drives. SSD drives are cheaper than RAM, so we charge you less to store it, but we charge you a bit more to retrieve it because we've got to do IO to go and get it. All right, so that's S3 standard IA. So infrequently accessed data. All right, so there you go, lower storage, higher retrieval. And then if you've got another data set that is, say, a development data set, or it's data set that can be easily recreated by running some kind of transform job or an ETL process or something like that. That one, we can put it in one zone IA. So by default, in a region, we know that there are multiple availability zones, right? Behind the scenes, when you put your one file up, S3 is going to make multiple copies of that in all available data center, not data centers, availability zones. All right. So I don't know how many copies we've got of that behind the scene, but I know for a fact that we can lose a complete availability zone and infrastructure from other pieces of the remaining infrastructure. In fact, does anybody know the really cool number for data durability in S3? Anybody heard this one? No? All right. Well, if I can find my mouse again.
It's availability or durability. Actually, it was 99.9999. 11 times 9, right? Something.
Yeah.
That's what you're talking about.
Right. So availability, the SLA for availability of the S3 API is 99.9. That's just the service. For the data that is stored in S3, this is your data durability SLA. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 nines durability. The way that equates is if you are storing 1 million objects in your bucket, AWS would contractually be allowed to lose one object every 10,000 years. So that's pretty high. So even if the service goes down, even if we lose an availability zone and some of the infrastructure, your data is durable. Anyways, I like those cool numbers. Anyway, so one zone IA, if you've got infrequently accessed or development data that can be easily recreated, then you can tell in the region, only store it in this availability zone. We'll still store multiple copies of it, but you pay slightly less than standard IA because it's only in one zone. But we're not done yet. There's another one. S3 intelligent tiering. So with all of these, to clear that, you can write what's known as a life cycle policy. So you can say, now, okay, this is a real scenario. You ready for this one? We all know that the internet runs on cat videos. Okay, we all know it. It used to be gaming and other unmentionable activities, but that's all been overtaken by cats. So let's say you're running a viral media company, because we all love those. And so they get these cat videos and they attach adverts to it, but whatever. So all of a sudden we get a video of Tiddles biting the nose of a dog. And it's the funniest thing the internet has ever seen. Now, clearly, we're okay with putting that in S3 standard. But what happens when we now get a new video of Tiddles taking a bath? Obviously, that is clearly the funniest thing the internet has ever seen. So this one now, it's been relegated to history. So we don't want to pay the full prices for that. So I would write a life cycle rule that says if a video has not been accessed for 30 days, move it to infrequently accessed. That's cool. We can then go further, and I'll expand on that in just a second. So maybe I want to do it even cheaper. Then I'll go into one zone IA, lower my cost. Of course, my retrieval costs are going up, but you know, really, I mean, who wants to see a cat biting a dog's nose? That's not funny, is it? Only cats taking baths are funny. So we have full programmatic control over where these objects are placed. Now, they don't move in the bucket. This is billing concepts, all right? Whatever we do to move them around behind the scenes is really of no consequence to you or me, but this is all billing. Now, what if you don't want to write those rules? What if you want something called S3 intelligent tiering? What that does is means you don't have to go and program the rules. What it does is it moves the data around based on access patterns. You do pay a small monthly fee for every object that's under management. You do pay a small fee, but you gain that back because it's moving it to the correct tier based on its intelligent rules. All right, so you don't have to write your lifecycle policies. There's another storage target. Actually, there's two. I'm going to put these ones together. We've got S3 Glacier and S3 Glacier Deep Archive. Anything that you would have put to tape, this is where they go. S3 Glacier is designed for very, very infrequent access, maybe 3 times a year, maybe. It's very, very low cost. We're down into the single-digit cents per gigabyte. I think it's very cheap. I'll show you that one. And I can say cheap on this one. But it's relatively expensive to retrieve it. So you really don't want to put things in S3 if you're going to retrieve it often. The other one is S3 Glacier Deep Archive. And that one is even cheaper, but you can't get your data back faster than 12 hours. Okay. The difference between the two is Glacier will allow you to retrieve it in a few minutes, but you will pay through the nose for it. You will pay extortionate amounts of money to get your data back, essentially, logically from tape within minutes. You do not have that option in Deep Archive, right? That is only slow retrieval. So it's the cheapest and the lowest retrieval cost as well. I straight up, I don't know. I don't know what happens behind the scenes. They don't tell us. I would imagine they do, but I don't know. All right, quick knowledge check. Everyone ready? Then we're going to hit databases. You want to store data that is infrequently accessed but must be immediately available when needed. Which one do we use? Okay, we've got a bit of a mix on this one. So we've got A, D, and C's and B's. All right, we have got complete coverage. Now I'm in. All right, let's go through it. So as we've got complete coverage, we'll actually go through this one. So is intelligent tiering a storage class? No, it's a mechanism. All right, so it's not that. S3 Glacier Deep Archive, does that suit the immediately available? Nope, so that one's out. S3 Standard IA, so it's immediately available. Yep. But it's infrequently accessed. Sounds like a winner to me. S3 Glacier, is it immediately available? No, we can get it back within minutes and we're going to pay through the nose for it. So that does not meet our requirements. So yeah, standard IA for that one. Okay, next up, file storage. File storage is exactly how you imagine it is if you are running on-prem and you've got your Z drive mounted to your corporate file server. Same kind of process. Or if you're in the Unix world, you got NFS mounts for your home directories and things like that. It is basically the same, right? Multiple clients accessing the same server, accessing those same files on that server, right? It's exactly the same. In fact, it's using exactly the same protocols. There's another one that's not on these slides, but I'll tell you anyway. So EFS is for your Unix workloads, and it uses NFSv4 and 4.1. Okay. Basically, you provision in the EFS system. You say, give me a mount point, and it appears in your subnets, and you mount it like a local server. But really, it's actually a distributed service behind the scenes. So your EC2 instance here and here, they access it through a local IP address in their subnet, but that goes back to a centralized system that is managed by AWS. Now, it's really cool. I used this for a while. And when you mount them into, I don't know, /home on a Unix system, it appears as an 8 exabyte size hard drive, which is really cool. Anyway, the data that is stored on this service is stored in multiple availability zones. So it's got, I think this one also has 11.9's durability, and it has storage classes like S3, and it has intelligent tiering like S3 as well. We're just accessing the data over the NFS protocol apparently inside our local network. Now, the other one that's not on here for you Windows people is Amazon FSx. That is a managed Windows solution that provides, DFS, shadow copies, basically your SMB mounts. All right, it's running on native native Windows, so you get all the benefits of those file system features for Windows. Not quite done yet. If you're doing high performance computing on Windows, there is FSx for Lustre. Lustre is a high performance distributed file system. But still not done. There is also FSx. This one is recently released with ONTAP. So if you're used to running NetApp workloads, then FSx, we can actually run ONTAP workloads as well. So that's pretty cool. I don't actually know too much about this one yet. It's relatively recently released. So that's pretty cool. I don't know if you're running any NetApp but a lot of enterprises certainly do. They're pretty amazing devices, I've got to say. All right. Quick breath. Any questions? This is the time of day when my throat starts getting a bit dry. We'll try and keep it going. All right, no questions. Let's move on to AWS databases. Now, I will say this is a three-day course in its own right. I love teaching this. It's called Planning and Designing Databases on AWS. Obviously, you know, we've got the rest of this module to do a 3-day RDS. Yes, there we go, Relational Database Service. That's only one of 15 database services available to you in AWS, which is pretty cool. All right, so fairly standard before we get into the actual products themselves. Relational databases and non-relational databases. That's a very gross breakdown of the database types. Non-relational databases have many subtypes. We're only really going to cover one, which is Dynamo. We'll show you that. Dyna. We'll cover that one. And on the relational side, we have RDS, as correctly said there, the Relational Database Service. Now, if you're a bit of a data dude, this will make some sense. If you're not, don't worry, this is a real quick bit nerdy. The way we store data in a relational database is we tend to go through an entity discovery process. Inside a relational database, this one would be products, right? Our entity is a product. Inside our database, we may also have an entity of users, orders, addresses, right? The list can go on. These are the entities. These are the things in our database, and we join them together with things called foreign keys. And we do that because we don't want any duplication of data within our database. They come from the 70s and they were designed with 70s technology in mind. They are still fantastic. I'm not putting them down. But this is typically how we store. So we've got a products table. We've got a users table, an orders table, an address table, and we link them all together through these foreign key relationships, and we do joins to get them back together to reconstitute a complete record. Think about if somebody places an order on your website. You need to know the product, you need to know the order, the address, and the user. I mean, probably a load more stuff as well. And so what we do when we write the data, we shotgun it all over, and when we retrieve it, we join it back together through the SQL language. All right, when it's done for storage efficiency. On the other side, we don't care about storage efficiency because when these NoSQL or non-relational systems were designed, the constraints that relational database designers had don't exist anymore. When relational database designers designed their databases, storage was cheap, small, no, it wasn't. It was expensive, small, and slow. All the things you don't want for a database. So they spent a lot of time designing the SQL language to optimize storage. Flip forward until relatively recently, NoSQL, oh, that's a total mess, isn't it? NoSQL databases don't have those constraints. What is storage these days? Storage is vast, storage is cheap, and it is fast. So we don't care about storage efficiency in non-relational databases. Instead of breaking up that order into multiple tables, we just store the entire record as a single record. Yep, non-relational will be document, key value, graph databases, ledger databases, exactly, all of those kind of things. Generally, relatively modern and without the constraints of slow, expensive, and small storage. So we don't care about storage efficiency. We just store the entire record in one record, okay, like that. So this would be one order. John Doe from this address ordered that. What was the other one? And we sent it to, you know, this, what was it, products. Anyway, you get it. So we store the entire record. So retrieving and storing this data is our access patterns are very different because we don't do joining. Anyway, could do this one for hours and days, but I won't do that. Oh, here we go. Look, there we go. So in a relational database, yes, we store things in tables that represent entities, and we join them together with the SQL language to reconstitute or rehydrate our data into a complete record. We have in Amazon managed database and managed relational database. We call it the RDS database service. RDS database service is there to do primarily one thing, is automate repetitive administration tasks. So think about your DBA. Do you want to be paying your expensive DBA, because we know DBAs are expensive? Do you want to be paying him to write backup scripts or verify that the NFS mount point on the backup server is valid? No, of course we don't. We want them to do what they're good at, which is get into the database, optimize the queries, optimize my data set, optimize my access patterns, and work with my development teams. That's what I want my DBA to do. So get rid of this undifferentiated heavy lifting, offload that to AWS, and you get on with managing the data. Other reasons to use it: yes, secure and transmit and store. So we've got integrated SSL certificates if you want them, encryption at rest. So EBS, one of the features of EBS volumes, we can do on-disk encryption. Sorry, underlying volume encryption. You don't have to do encryption at the operating system level. The other one is they're designed for the cloud. So we've taken away things like HA. No, we haven't taken it. We've taken away the responsibility from you. So HA, failover, backups, synchronizing primary, secondary, setting up read replicas, all that administrivia, patching, updating, operating install, all that, it's all gone. You concentrate on the data, stay there, right? Now, at this point, we haven't really talked about a particular database server. We're talking about the service and all the commonality and like the common features. But what we do is implement six different engines. Aurora was written by us and it's cloud native. And on the wire, it is Postgres and MySQL compatible. All right. So that's one engine, is Aurora. Another engine is Postgres. Then we've got MySQL, MariaDB, Oracle, and Microsoft SQL Server. Obviously, these ones are commercial databases. You can bring your own licensing, or you can use built-in licensing as well, right? So it's up to you. You have options. Now, depending on the engine, they do implement certain things differently. Like replication is different on Microsoft SQL Server than it is on MySQL. But this stuff is the commonality is the service commonality before we implement engine-specific features. And you have access to most of the engine-specific tunables, say with Oracle and MySQL, all of them, through what we call parameter groups. You don't have direct access to the actual database server, but you can program it and configure it via parameter groups. All right. So, Aurora, this one was written by us. And like I said, on the wire, it is Postgres and MySQL compatible. So you can switch from a workload that's designed for MySQL to Aurora with 99.999% of the time, zero changes at all. No, we don't support DB2. No, we don't have that. It's only these engines here. Unfortunately, I get that question quite a lot. So Aurora. Aurora was written by us to operate in the cloud. Standard RDS, you have a primary database server and you have EBS volumes that hold the data, right? And then when you have a secondary server, you have another. Oh, that made me jump. Who was that? That's okay. You made me jump. Right. So we've got a primary and we've got a secondary, and each one has copies of the data. Then you have read replicas. We love them. We love them. Okay. There we go. So that's our database cluster. All right. So now how many copies of my data do I have? Well, right now I've got 3, one there, and one there. And I'm going to pay for it. Okay. I pay for this EC2 instance and I pay for the storage. I pay for the EC2 instance and I pay for the storage. You get the point. I pay for that and I pay for that. Now, Aurora has a completely different take on it. We still have servers, so we still have a primary, but now I have a distributed storage volume. So the compute connects to the distributed storage volume. The secondary connects to that. The read replicas connect to that. Okay. So now our primary, where all writes are directed, has to do no replication, no IO work, no well, loads of other things. Not going to get, well, see, I can get really passionate about this one. Anyway, so what we're doing is offloading a lot of the responsibility that would be on a primary database server, and we're putting it in the storage layer, and we're not replicating data. So Aurora is designed to operate in a modern cloud environment. There you go. Reduce database cost by eliminating unnecessary I/O. I/O is a big blocker inside a kernel. The less you have to do, the more productive work you can do instead of just busy work. All right. And then this distributed storage volume is spread across the availability zones in a region, and the data is behind the scenes replicated 6 times. All right. The servers themselves, they don't care about that. They just write and they just read. As a write goes down into there, it's available to read up there. Isn't that cool? It's much better than running disks. Anyway, so that is Aurora. Funky numbers, 5 times the throughput for MySQL workloads, 3 times the throughput for Postgres workloads. And if you're interested, come and join me on a planning and designing database course where we go a much deeper dive on Aurora. Okay. Ready? Read the question. What have we got? One of the employees at the office shop has an idea for a new inventory management system. They believe they should maintain the data in a text file in S3. What do you think? Yes or no? What is S3? Yep, that's what it says. Should we store the data in a text file in an object store? No. Put it in a database. Yeah, of course. Frequent changes. Good point. Yes. Now, while we can write frequently to S3, remember it works on the whole file level. So if I want to update a row and my data set is now 20 gigs in size, I've got to do a 20 gig write every time. That sounds like a downside, but trust me, for S3, that's the way it works. It's a worm type scenario. Read once, write. No, hold on. Wrong way around. Write once, read many. Yes, put it in a database, of course. All right. What about a non-relational engine? We're really going to talk about DynamoDB here, but so we've looked at the use case. All right, we do not care about normalizing data. All right, that's the process we go through when we're creating these entities, and we go through that. 3NF is the gold standard. All right, splitting apart, make sure we've got no duplicates, maybe making sure we're not overloading one field with multiple different data types. There's a whole ecosystem, a whole process around normalizing data in a relational database. Non-relational databases, we don't care about that. Essentially, this is denormalized data. All right. So instead of doing these entities in different tables joined through foreign keys, it's just a single record. All right. So it uses structures other than rows and columns to organize the data. In Dynamo, which we're going to see at the moment, essentially, Dynamo is a key value pair. The way you access your data is by the key. Really, we don't care about the values. DynamoDB does not care about the values as such. What I would do if I want to retrieve this record is I would say, give me 1. Your application will retrieve the record, and then your application will manipulate the data how it sees fit. But essentially, that's what we're looking at. One of the non-relational database engine types is a key value database. And that's what we're going to look at with DynamoDB. Oh, did it say in there? No. All right. And one of the good things about is because we only store and retrieve, I had a brainstorm then, store and retrieve data by the key. And like I said, the value makes no difference. What it means, the schema, this schema here is completely flexible. All right. Key number 1 could be an order receipt. Key number 2 could be an address. Key number 3 could be a transaction. Now, there are ways to design these keys, and again, it's way beyond the scope of this course, but so it's a schemaless. We call DynamoDB a schemaless NoSQL key value pair, key value database. All right, let's have a look at Dynamo. Dynamo, the service. Dynamo came from Amazon.com's desire to get off of Oracle and pay very expensive licensing. What they did, Amazon is a data-driven company, and they said, why am I paying so much money to Oracle? As probably many people do. And so they said, well, because, you know, it's a database and we need a big database. And then somebody else said, yeah, but do we need all the features of this very expensive database? They went, oh, I don't know, let's find out. So all of this story is really what I'm saying is we analyzed the query traffic going into the database. And they break it down into 3 categories. 1, complex querying. 2, one-way joins. And 3, key value lookups. Because we've all done it. Like you go select star from users where username equals Bob. That is essentially a key value lookup, right? Our one key is Bob, right? Guess the percentages. What do you think were complex querying? Like nested sub-select, joins, outer joins, inner joins. I don't know. What do you think? Less than 5? 10%? Pretty cool. 5%. What do you think were one-way joins? So join on one table on another. John's in there. Okay, ready for this? So we've got complex, we've got simple, and key value. All right, so complex was 5%. Simple one-way joins, 15%. Single key value lookups, 80%. Yeah, it'd be really interesting if you do it on your databases as well. So think about it. There is 0 functionality in any database differentiates it between a key value database. None whatsoever. There is no difference in a one-way lookup and a key value lookup in Oracle than there is in any other database. So why are we paying? And that was the big driver to develop DynamoDB. All right. Pretty cool numbers, huh? So DynamoDB is designed as a fast, oh, hold on, it's designed per table, its design criteria is 10 trillion requests per day. The cool thing, one of the cool things is essentially you have endless capacity, endless storage, and endless performance at any scale. Relational databases get slower over time. It's just a fact. It's not a knock. The more data you put in them, the slower they get because they have to do re-indexing and scanning and, you know, and table lookups and all that kind of stuff. They do get slower. DynamoDB does not get slower the bigger it gets. It maintains fast, single-digit response times at any scale. There are always caveats on how you design the service, but well, I'll cover that in a different course if you want to come and join me. But anyway, that's what it is. It's serverless as well. You just interact with it over HTTP. Give me that, put that. That is basically it. Gets and puts. Anyway, I love Dynamo. You can probably tell. All right. How do I move data? Right, I've convinced you. You're like, oh, Aurora sounds cool. 3 times the performance for exactly the same. Awesome. Dynamo, brilliant. We'll have some of that. How do you get your data in and out? Well, couple of options. We've got the database migration service. Essentially, DMS deploys an agent and it connects to the source database and it moves your data to the destination database. It's designed for, and let me get these the right way around, it's designed for homogeneous migrations. All right, so like for like. So we said that Aurora is MySQL compatible, so you can go MySQL through the migration service and push it on. All right, essentially it sets up a replication client there and moves the data over there. What about if you want to move from Oracle to Postgres? Well, we have another service, it's not on the slides, but we have another service called the SCT, which is the schema conversion, tool. That's it, schema conversion tool. Essentially, it kind of sits in the middle and programs the DMS agent. And really what you do is you say, right, this is an Oracle database and this is a Postgres database, and it understands the differences between things like naming conventions. And I'll make this one up because I can't remember. Maybe, for example, Oracle is all capitals for its table names. And maybe Aurora Postgres starts with underscore and must be lowercase. So it can do those kinds of translations. And it can change the data types as well. So if it's called a big int in one and it's called an int5 in the other, it can make those changes on the fly. So that's your schema conversion tool. Hold on, there's another one. Don't think we did. All right, so DMS. Imagine you've got a 200 terabyte database. Do you think replicating that with an agent over a leased line or the internet for 200 terabytes is a good idea? Not really. This is where the coolness, this is where the serious cool factor comes in. All right. We have something called the Snow family. Not Jon Snow from, up north, but the Snow family. Snow family has 3 members. We have a Snow Cone, which is an 8 terabyte hard drive that we will ship to you, ruggedized. You copy your data onto it, you send it back to AWS, and we copy it to S3 for you. That's one. The other one we got is a Snow Ball. That is an 80 terabyte ruggedized appliance that has compute built into it. So what that means is, remember I said we deploy an agent, we put the agent on the Snowball device and we copy your data to that, and then you put it on UPS, and then it gets ingested into your database, right? And it's faster. And I know this, I said 200 terabytes and this one is 80, but we can deploy them in multiples of, but we're not done yet. Imagine if you had a 10 petabyte data set, and they exist, by the way. We have another one called Snowmobile. And that is the entry point to engaging the Snowmobile team is 5 petabytes. And it's an articulated truck that backs up into your data center. You pull the cables out the back, you plug them in, and you copy your data to it, and then they drive it to AWS. That is so cool. Anyway, so you've got options. Pretty wow, huh? Yeah. I'm gonna show you. How do you mean outrageous? Fabulous. It's fabulous. All right, so AWS Snowmobile. Yes, you can do data extraction as well. Absolutely. Yep. Images. Here we go. Let me just bring this over. 1 second. I want to see the picture. Ah. Okay, ready? That is one AWS Snowmobile. That individual truck can carry 100 petabytes of data. Oh, wow. I worked on a project. Oh my God, there's a Lego one. Look at that. There. Ah, brilliant. I'm gonna have to get one of those. I worked on a project out of New York to move a big imaging company to AWS, and they had 4.4 petabytes of data, and I couldn't get a snowmobile to go to their data center. I was very upset. I really wanted one. Anyway, yes, so there you go. That's some of your big data migration solutions. What does Snow? I don't think it stands for anything in particular. I'm not sure why it's called Snow. Maybe you freeze the data while you transport it. I'm not sure the reasoning, but it's pretty cool. Whatever the reasoning, I love it. All right. Okay, so that's database migration service. All right. Quick, another one of these wire things up. So storing data in a relational database. Serverless, oh, sorry, yeah, storing data in a relational database. Is that RDS or DynamoDB? Obviously, you got that one. Yep. Running a serverless database. Dynamo. Now, I'm gonna muddy the waters here. You can actually run serverless relational database service. Aurora serverless. Okay. There is Aurora serverless. Okay, you pay for it differently. There are no servers to manage. You access it, but it's all managed by AWS. Just wanted to let you know in case anybody's read it. Okay, next one, storing data in a key value database, RDS or Dynamo? Dynamo. Using SQL to organize your data, RDS. Scaling up to 10 trillion requests per day.
Dynamo.
Dynamo, yeah. And lastly but not least, storing it in an Aurora database. Does anybody a math whiz could tell us the transactions per second for a 10 trillion? So it's what? I don't know what that would work out to. There's 86,400. All right. Anyway, whatever. It's a lot of transactions per second. So yeah, it's a very high performance system. Sorry, yes, the last one was RDS. All right. There are other database services. A real brief intro into these: Redshift, petabyte scale, and actually exabyte scale analytics engine. So OLTP, no, OLAP, online analytics programming, OLAP workloads. That's your that's your data warehousing. DocumentDB for running MongoDB workloads. It's a managed FYI. Oh, awesome. Yeah, get on those if you're into the analytics side. Redshift is an amazing product. Neptune for your graph databases. So you're running graph databases. You want to run recommendations engines, highly, so not a relational engine, highly relational data, all right? Graph databases. QLDB, quantum ledger database. So cryptographically verifiable, immutable, append-only database. Loads. Another one, managed blockchain. You want to do distributed blockchain? We've got a managed solution for that. Elasticache. Elasticache is primarily used to cache between a database and an application server. We also have another couple on here. So we've got a DAX, which is the DynamoDB accelerator. So if you want to make Dynamo go even faster, you put DAX in front of it. That caches the results. We're also missing from here. Oh, can't spell. Let's clear that. MemoryDB, which is a managed Redis. There's also TimeStream for time series databases. There is also key spaces for your Cassandra compatible workloads. So as you can see, there are lots of database choices. Why do you want so many database choices? So that you make the right database choice. don't force everything into that one database solution that you know. Don't do that. Anyway, let's do a knowledge check before we take a brief break. Everyone ready? Which S3 storage classes are optimized for archive data? B and D, correct. Yes, Glacier and Deep Archive. Kind of in the title, really. Which option is true about EBS volumes and EFS file systems? Bit more reading to do on this one. Got one D. Kunwa's in there first. B. A D and a B. Put you out your misery on this one. This one is actually A. So EBS volumes, remember what that is? It's your local hard drive. So a local hard drive is stored in a single availability zone. We can copy it other places, but it is stored in a single availability zone. EFS is we store that data across multiple availability zones. Okay, so that's the difference between the two. A customer wants to store data in an object storage service. Which one is that? Yep, S3. Which statement describes DynamoDB other than awesome? Oh, that's not up there. Yep, we've got a B in there. Yep, well done. Serverless key value database. Which service is used to query and analyze data across a data warehouse? Redshifty. Love it. Yes, that is Redshifty. Brilliant. All right, how are we doing for time? Let's take a 5-minute break. So we got 3:05. We'll move on to the next one. Redshifty, brilliant. Made my day.